Here's the thing about Earth. Every 100,000 years, like clockwork, the planet freezes. Ice spreads from the poles. Glaciers march across continents. Sea levels drop hundreds of feet. Entire ecosystems shift toward the equator. Then, just as predictably, the ice retreats. The planet warms. Life spreads back north and south. This has happened over and over for millions of years. The pattern is so regular you could almost set your watch by it. Almost. Because here's what makes this truly strange. The cycle isn't quite perfect. It's close. Incredibly close. But there are wobbles, variations, times when the ice should have advanced but didn't, times when it should have retreated but lingered, and nobody knows exactly why. If you're using this to fall asleep, that's exactly why I make these videos. Maybe subscribe and let me know where you're watching from and what time it is. I always check the comments and it's fascinating. We know the ice ages happen, we can measure them. In ice cores drilled from Antarctica, in ocean sediments pulled from the deep sea floor, in the rocks scraped and carved by ancient glaciers. The evidence is everywhere. We even know some of the reasons. Earth's orbit changes shape. The planet wobbles on its axis. The tilt shifts slightly. These changes affect how much sunlight hits different parts of the planet. They create cycles, predictable patterns in the amount of solar energy reaching Earth. But here's the problem. Those orbital changes alone aren't enough. The math doesn't quite work. The wobbles in Earth's orbit should create temperature changes of maybe 1 or 2 degrees. Instead, we get ice ages, full glacial periods where ice sheets cover half of North America, where the climate shifts so dramatically that entire species go extinct, or evolve, or migrate thousands of miles. Something is amplifying the signal, taking those small orbital nudges and turning them into massive climate swings. Scientists have been trying to solve this puzzle for over a century. They've proposed dozens of theories, some elegant, some bizarre, some that seem perfect until new evidence proved them wrong. The answer, it turns out, involves everything. The oceans, the atmosphere, the ice itself, carbon dioxide locked in rocks and released by volcanoes, dust blown from deserts, plankton in the sea, forests spreading and retreating, all of it connected in ways we're still figuring out. And the really unsettling part, we're living in one of the warm periods right now. Between ice ages, the ice will come back, maybe in 10,000 years, maybe in 50,000. This cycle isn't done, unless we've broken it, which is a whole different question. The first person to really understand that ice ages happened wasn't a scientist. He was a Swiss carpenter and hunter named Jean-Pierre Perraudin. The year was 1815. Perraudin spent his days in the Alps, guiding travellers through mountain passes. He noticed something strange. Huge boulders sat in the middle of valleys, miles from any cliff they could have fallen from. The rocks didn't match the stone around them. They were granite, but the valleys were limestone. Perraudin had a theory. The glaciers had carried them. He told this to a Swiss engineer named Ignaz Venetz. Venetz laughed. Everyone laughed. Glaciers moved slowly, maybe a few feet per year. How could they possibly carry boulders the size of houses across entire valleys? But Perraudin was persistent. He showed Venetz the scratches, long grooves carved into solid rock, all pointing the same direction, down from the mountains. Venetz started paying attention. He looked at the boulders again. He measured the scratches. He talked to other mountain people. They all said the same thing. The glaciers used to be much bigger. You could see where they'd been. The evidence was everywhere. Venetz became convinced. He presented his findings to the Swiss Society of Natural Sciences in 1821. Most scientists dismissed him. Few listened. One was a young geologist named Louis Agassiz. Agassiz was sceptical at first. He went to the Alps to prove Venetz wrong. He spent the summer of 1836 studying glaciers, measuring them, watching how they moved, looking at the rocks they carried. He came back convinced that Venetz was right. More than right. The glaciers hadn't just been bigger, they'd covered most of Europe, all of Scandinavia, much of Britain, parts of Germany and France and Switzerland. Agassiz called it the Ice Age, die Eiszeit in German. He presented his theory in 1837. The scientific community was not impressed. The problem was the dominant theory of the time, catastrophism. The idea that Earth's features were shaped by sudden violent events. Most geologists believed in the biblical flood. They thought the boulders had been carried by rushing water. The scratches were from debris in the floodwaters. Everything could be explained by one great deluge. Agassiz was proposing something different. Slow change, gradual processes, ice advancing over thousands of years. It contradicted the prevailing view, but Agassiz had evidence. He showed colleagues the polished bedrock, the parallel scratches, the U-shaped valleys carved by ice, the moraines, long ridges of debris left when glaciers retreated. You couldn't explain all of this with a flood. Slowly, scientists started to accept it. Charles Lyell, the most influential geologist of the era, was convinced by 1840. He saw the evidence in Scotland. Scratched rocks, erratic boulders, glacial valleys, it all fit. By 1850, the Ice Age theory was mainstream. But scientists thought there had been only one ice age, one period when glaciers covered the northern continents. Then they melted. End of story. The next discovery changed everything. In the 1860s, geologists started finding multiple layers of glacial deposits. In some places there were clear boundaries, old glacial debris, then a layer of soil and plant remains, then more, glacial debris, then another soil layer, then more ice deposits. Each layer represented a different climate. Glacial periods separated by warm periods. There hadn't been one ice age, there had been many. James Geekie, a Scottish geologist, documented this in detail. He identified at least 4 separate glacial periods in Scotland, each separated by warmer interglacial periods when plants grew and soils formed. The evidence kept mounting. In the Alps, geologists found the same pattern. Multiple glacial advances, each one pushing rock and debris downhill, each retreat leaving behind distinct deposits. In North America, the evidence was even clearer. The Great Lakes region showed layer after layer of glacial till, different ice sheets at different times, some reaching as far south as Missouri, others stopping in Wisconsin or Minnesota. But how could anyone prove this? How could you date rocks that were hundreds of thousands of years old? Radiocarbon dating wouldn't be invented until the 1940s, and it only worked on organic material less than 50,000 years old. The breakthrough came from an unexpected place: the ocean floor. In the 1950s, oceanographers started drilling cores from the deep sea, long cylinders of sediment pulled up from the bottom of the ocean. These cores contained the shells of tiny organisms called foraminifera. Forams for short. Forams are single-celled creatures. They build shells from calcium carbonate. When they die, the shells sink to the ocean floor, layer after layer, year after year, for millions of years. Here's what made them useful. The shells contain oxygen, specifically oxygen isotopes, oxygen-16 and oxygen-18. The ratio between these two isotopes depends on temperature. When the world is cold and ice sheets are growing, more oxygen-16 gets locked up in ice. That leaves more oxygen-18 in the ocean. Forams building shells during ice ages incorporate more oxygen-18. When the ice melts, the ratio shifts back. Scientists could measure these ratios. They could see the ice ages in the forum shells. Each layer of sediment represented a different time period. You could read climate history like a book. Cesare Emiliani did exactly this in 1955. He analysed forum shells from Caribbean sediment cores. He found a clear pattern, warm periods and cold periods alternating, over and over, going back hundreds of thousands of years. He identified what he called oxygen isotope stages, odd numbers for warm periods, even numbers for cold periods. Stage 1 is now our current warm period. Stage 2 was the last ice age. Stage 3 was a cooler period before that, and so on. The pattern was remarkable. The ice ages weren't random. They followed a rhythm, a cycle. Roughly 100,000 years between major glacial periods, with smaller variations in between. Other scientists confirmed this. They drilled cores from different oceans, the Atlantic, the Pacific, the Indian Ocean. Everywhere they looked, they found the same pattern. The same cycles, the same rhythm of ice ages. Then came the ice cores. In the 1960s, scientists started drilling into the ice sheets of Greenland and Antarctica. These weren't like ocean cores. Ice cores contained actual ancient atmosphere, tiny bubbles of air trapped when the snow fell and compressed into ice. You could measure the carbon dioxide in those bubbles, the methane, the temperature when the snow fell. You could see volcanic eruptions as layers of ash. You could count the annual layers like tree rings. The first deep ice core came from Camp Century in Greenland, drilled between 1963 and 1966. It reached bedrock at 4,160 feet. It contained ice over 100,000 years old. The data confirmed what the ocean cores showed: regular cycles of warming and cooling, ice ages followed by warm periods, over and over. But the ice cores revealed something the ocean cores couldn't: the speed of change. Some transitions from ice age to warm period happened incredibly fast, within decades, maybe even years. The climate could flip like a switch. In the 1990s, the Greenland Ice Core Project and the Greenland Ice Sheet Project 2 drilled even deeper cores. They found ice nearly 250,000 years old. The Antarctic cores went back further. The Vostok core, completed in 1998, reached ice 420,000 years old. Later cores from Dome Sea and Antarctica went back 800,000 years, 8 ice ages, 8 warm periods, all recorded in the ice. The pattern was undeniable. Scientists could now see the details. Each ice age wasn't uniform. There were cold periods and slightly less cold periods, advances and retreats. The climate wobbled even during glacial times. And the warm periods, the interglacials, weren't all the same either. Some were warmer than others, some lasted longer. Our current warm period, the Holocene, has been remarkably stable. Unusually stable compared to previous interglacials. The evidence was overwhelming. Ice ages happened. They happened regularly. They followed a pattern. And we were living in a warm period between them. But knowing that ice ages happened wasn't the same as knowing why. The discovery of the pattern just made the mystery deeper. What could cause such regular cycles? What force was powerful enough to freeze half the planet every 100,000 years? That question would take another set of discoveries to answer. And even then, the answer would be incomplete, because the more scientists learned, the more complex the picture became. The ice ages weren't just about ice. They were about everything. The whole Earth system responding to some trigger. Some combination of triggers, all working together in ways that scientists are still figuring out. It's kind of perfect, actually, learning about ice ages while you're trying to sleep. These massive slow changes that happened over thousands of years. Nothing urgent, nothing that requires you to stay alert. Just the Earth doing what it's always done. Freezing, thawing, freezing again. Let the pattern carry you. The rhythm of it. 100,000 years is a long time to wait between ice ages. You got nothing but time right now. Here's the thing about orbits. They're not perfect circles. Earth doesn't glide around the sun like a ball on a string. It wobbles, it tilts, it shifts. And these tiny changes over thousands of years add up to something massive. Ice ages. A Serbian scientist figured this out in the 1920s. His name was Milankovitch. He was an engineer, a mathematician, a prisoner of war who did calculations in his head to stay sane. And he discovered something nobody else had seen. Earth's orbit changes, not randomly, in patterns, predictable cycles that repeat over and over, and when these cycles line up just right, the planet freezes. 3 cycles, 3 different wobbles, each one operating on its own schedule. The first cycle is about the shape of Earth's orbit. Right now, our path around the sun is almost circular. Almost, but not quite. It's slightly oval, stretched out. This shape changes over time, sometimes more circular, sometimes more stretched. The cycle takes about 100,000 years. When the orbit is more circular, Earth stays about the same distance from the sun all year. When it's more oval, we swing closer in summer and farther away in winter. The difference isn't huge, but it matters. The second cycle is the tilt of Earth's axis. Right now, our planet leans at 23.5 degrees, like a top spinning at an angle. This tilt gives us seasons. When the northern hemisphere tilts toward the sun, it's summer there. When it tilts away, winter. But that angle changes. Over 41,000 years, Earth's tilt shifts between 22.1 and 24.5 degrees. More tilt means more extreme seasons, hot summers, cold winters. Less tilt means milder seasons, cooler summers, warmer winters. And here's what matters for ice ages. It's not about how cold winter gets, it's about how cool summer stays. Ice builds up in winter, that's normal. But if summer isn't warm enough to melt it all, the ice stays, year after year, building, thickening, spreading. Less tilt means cooler summers, which means more ice survives, which means glaciers grow. The third cycle is the wobble of Earth's axis itself. Imagine a spinning top. As it slows down, it wobbles. Earth does the same thing. Our axis traces a slow circle in space. One complete wobble takes 26,000 years. This wobble changes which season happens when Earth is closest to the sun. Right now we're closest in January. Northern Hemisphere winter. In 13,000 years we'll be closest in July. Northern Hemisphere summer. This matters because it affects how extreme the seasons are. If you're closest to the sun during summer, that summer gets even hotter. If you're farthest away during winter, that winter gets even colder. 3 cycles, 3 wobbles, each one changing how much sunlight hits different parts of Earth at different times of year. Milankovitch calculated all of this by hand with tables and charts and endless equations. He figured out exactly how much sunlight reached Earth at different latitudes during different seasons over the past 600,000 years, and he found a pattern. Every 100,000 years the cycles lined up. The orbit became more oval. The tilt decreased. The wobble put the northern hemisphere farthest from the sun during summer. All at once. Less sunlight in summer. Cooler temperatures. Ice that didn't melt. Glaciers that grew and grew and grew. He published his theory in 1920, then refined it in 1930, then wrote a whole book in 1941 called Canon of Insulation and the Ice Age Problem. Nobody paid attention. The scientific community ignored him. His math was too complex, his ideas too different. He was from Serbia, not a major research centre, and World War II was happening. Nobody had time for theories about ancient ice. Milankovitch died in 1958, still mostly unknown, his work gathering dust. Then in the 1970s, scientists started drilling ice, cores, long cylinders of ice pulled from Antarctica and Greenland, ice that had been building up for hundreds of thousands of years, layer after layer, each one a snapshot of Earth's ancient atmosphere. They could measure everything: temperature, carbon dioxide levels, dust in the air, pollen from plants, volcanic ash, all preserved in the ice like a frozen library, and they found cycles. The ice showed clear patterns, warm periods, cold periods, repeating over and over, and when they measured the timing, it matched Milankovitch's predictions almost perfectly. 100,000 years between major ice ages, 41,000-year cycles in the tilt, 26,000-year wobbles in the axis, all there in the ice. Undeniable. They also drilled cores from the ocean floor, sediment that had been building up for millions of years. Each layer contained tiny shells from plankton. These shells recorded the temperature of the water when the plankton lived. Warmer water, different chemistry in the shells. Colder water, different chemistry again. Same patterns, same cycles, same timing. Milankovitch was right. 30 years after his death, the evidence proved it. But here's the strange part. The orbital changes don't actually change the total amount of sunlight Earth receives. Not really. The planet gets about the same energy from the sun whether the orbit is circular or oval, whether the tilt is steep or shallow. What changes is where that sunlight goes, and when. More sunlight at the equator, less at the poles. More in summer, less in winter. The total stays the same, but the distribution shifts, and that's enough. That tiny redistribution of sunlight is enough to trigger an ice age. Think about it. The difference in sunlight between an ice age and a warm period is only about 0.1%, 0.1%. That's all it takes. Earth's climate is balanced on a knife edge. A tiny push one way starts the ice growing. A tiny push the other way melts it back. The orbital cycles provide those tiny pushes. Regular, predictable, inevitable. But there's something weird about the 100,000-year cycle. It's the strongest pattern in the ice core data. The most obvious rhythm, but it shouldn't be. The orbital eccentricity, the stretch of Earth's orbit, has the weakest effect on sunlight. Way weaker than the tilt cycle or the wobble cycle. Yet it dominates the ice age pattern. Scientists call this the 100,000-year problem. Why does the weakest cycle create the strongest effect? Nobody knows for sure. There are theories. Maybe the other cycles amplify it somehow. Maybe feedback loops kick in. Maybe ice sheets themselves create momentum that takes 100,000 years to build and break. Ice is heavy. Really heavy. A mile-thick glacier weighs trillions of tons. That weight pushes down on the Earth's crust. The land actually sinks under the ice. When the ice melts, the land slowly rises back up, but it takes thousands of years. Maybe that delay matters. Maybe the ice builds up over 90,000 years, slowly, gradually, getting thicker and heavier. Then something tips it over the edge. The ice collapses. Not all at once, but fast compared to how long it took to build. Within 10,000 years, it's gone. Then the cycle starts again. The Milankovitch cycles are still happening. Right now. Earth is still wobbling, still tilting, still changing its orbit. The cycles never stop. Right now, we're in a warm period. An interglacial. The ice sheets have retreated to Greenland and Antarctica. Sea levels are high. The climate is relatively stable. But according to the cycles, we should be heading back toward cold. Slowly. Over the next few thousand years, the wobbles should align again. Summer sunlight at high latitudes should decrease. Ice should start building up. Except it's not happening. Earth is warming. Fast. Faster than any natural cycle would predict. That's us. Human activity. Carbon dioxide from burning fossil fuels, changing the atmosphere in ways that overwhelm the natural cycles. We've broken the pattern. For now. Whether that's good or bad depends on your perspective. Ice ages are hard to live through, but rapid warming creates its own problems. The Milankovitch cycles are still there, still operating, still wobbling Earth's orbit and tilt and axis. But we've added a new factor, a new force, and nobody knows exactly how it will play out. Will we delay the next ice age? Cancel it entirely? Or just postpone it until the carbon dioxide levels drop again thousands of years from now? The math that Milankovitch did by hand in the 1920s is still valid. The cycles are real, the patterns are clear. But we've added a variable he never considered. Human civilization, industrial emissions, the ability to change our own planet's climate. The wobbles continue, silent, slow, inevitable. Earth keeps tilting and spinning and circling the sun. The same cycles that have driven ice ages for millions of years. But now we're part of the equation too, and the next chapter of Earth's climate story is being written by both natural cycles and human choices. The ice remembers everything. Every wobble, every tilt, every shift in Earth's orbit, trapped in those frozen layers, waiting to tell its story to anyone who drills deep enough to listen. So how do wobbles in space actually create ice on Earth? It seems impossible. Earth tilts a bit more, the orbit stretches slightly, and suddenly glaciers appear. Miles thick, covering entire continents. The connection isn't obvious, but it's real. And it all comes down to one thing. Summer, not winter. That's the weird part. You'd think ice ages start because winters get colder, more snow falls, temperatures drop, ice builds up. But that's not how it works. Ice ages start because summers get cooler, just a little bit cooler, not enough to notice day to day. But enough that last winter's snow doesn't completely melt. Think about it. Snow falls every winter in Canada, in Alaska, in northern Europe. Feet of it. But every summer, most of it melts. The cycle resets. Winter adds snow. Summer removes it. Balance. But what if summer can't finish the job? What if the temperature stays just cool enough that some snow survives? Not all of it, just patches, in valleys, on north-facing slopes, places where the sun doesn't hit quite as hard. That leftover snow sits through the next winter. More snow falls on top. The old snow gets compressed, turns to ice, gets heavier, denser. Next summer comes. Still a bit cooler than normal. More snow survives. More ice builds up. Year after year, decade after decade, century after century. The ice grows. At first it's just snowfields, then ice patches, then glaciers, small ones in the mountains. But they keep growing, spreading, flowing downhill like frozen rivers. And here's where it gets interesting. Ice changes everything around it. White surfaces reflect sunlight. Fresh snow reflects about 80% of the sun's energy back into space. Dark. Surfaces absorb it. Forests absorb about 90% of sunlight. Ocean water absorbs about 95%. So when ice covers the ground, less heat gets absorbed. The area stays cooler, which means more ice survives the next summer, which means more sunlight gets reflected, which means even cooler temperatures. It's a feedback loop. Ice creates conditions that make more ice. Scientists call this albedo feedback. Albedo just means reflectivity. High albedo equals more reflection. Low albedo equals more absorption. A forest-covered landscape has low albedo, dark green trees soaking up sunlight, warm ground. Snow melts quickly in spring. That same landscape covered in ice has high albedo, bright white surface bouncing sunlight away. Cool ground, snow barely melts at all. The Milankovitch cycles don't create much cooling on their own. The change in sunlight is tiny, less than 1%, but they trigger the feedback loop. And the feedback loop does the heavy lifting. It starts in the far north, northern Canada, Scandinavia, Siberia. These places are already cold, already get snow every winter. They're right on the edge, just barely melting all their snow each summer. When the orbital cycles reduce summer sunlight by even a tiny amount, these places tip over. Snow starts accumulating. Ice begins growing. The ice spreads outward, south from the Arctic, down through Canada, across northern Europe, into Russia. Glaciers thousands of feet thick, moving, grinding, reshaping the land. And as the ice spreads, it reflects more sunlight, which cools more area, which allows more ice to form farther south. The feedback loop accelerates. But there's another feedback loop happening at the same time. In the ocean, cold water holds more dissolved gas than warm water. You can see this with soda. Cold soda has more fizz, warm soda goes flat. Same principle with ocean water and carbon dioxide. As Earth cools, the ocean absorbs more CO2 from the atmosphere. Less CO2 in the air means less. Greenhouse effect. Less greenhouse effect means cooler temperatures, which means the ocean absorbs even more CO2. Another feedback loop, this one involving the whole planet's chemistry. Scientists can measure this in ice cores, tiny bubbles of ancient air trapped in Antarctic ice. Each bubble is a sample of Earth's atmosphere from thousands of years ago. During ice ages, CO2 levels drop to about 180 parts per million. During warm periods, they rise to about 280 parts per million. The pattern is clear. Less CO2 equals colder climate. More CO2 equals warmer climate. The Milankovitch cycles start the process. But the feedback loops amplify it. Turn a tiny change in sunlight into a massive change in climate. It takes time, though. A lot of time. The ice doesn't appear overnight. It builds gradually. Over thousands of years. Each summer leaves a bit more snow. Each winter adds another layer. The ice sheet grows inch by inch, year by year. Imagine living through the start of an ice age. You wouldn't notice, not in your lifetime. Maybe summers feel slightly cooler. Maybe snow lingers a bit longer in the mountains, but nothing dramatic, nothing obvious. Your grandchildren might notice more. The snowline creeping lower, glaciers in the mountains getting bigger, winters lasting longer. 1,000 years later, the changes are undeniable. Glaciers have advanced miles, forests have retreated, the climate has shifted. 5,000 years later, ice covers half the continent. Everything has changed. The ice builds fastest at the beginning, when it's small and only in the mountains. Then it slows down as it gets bigger. Spreading across flat land takes longer. The ice has to flow, push outward under its own weight. At its peak, the ice sheets are 2 miles thick in places. The weight is incredible. So heavy it pushes the Earth's crust down. The land actually sinks hundreds of feet under the ice. All that ice has to come from somewhere, from the ocean. Water evaporates from the sea, falls as snow on the ice sheets, gets locked up in glaciers, doesn't return. Sea levels drop. During the last ice age, the ocean was 400 feet lower than today. Coastlines were completely different. Land bridges appeared. Britain connected to Europe. Alaska connected to Russia. You could walk between them. The ice keeps growing until something stops it, until the feedback loops reverse. And here's the thing. The same orbital cycles that triggered the ice age eventually end it. Earth keeps wobbling, the tilt changes, the orbit shifts. After tens of thousands of years, the cycles swing the other way. Summer sunlight increases, just a tiny bit, but enough. The ice starts melting at the edges, slowly at first, just the southern margins. But melting creates its own feedback loop. As ice melts, it exposes dark ground underneath. Dark ground absorbs more sunlight, which creates more warming, which melts more ice. The albedo feedback runs in reverse. The ocean warms up slightly, releases some of that dissolved CO2, more greenhouse gases in the atmosphere, more warming, more melting. The ice that took 90,000 years to build can collapse in 10,000 years, sometimes faster. The end of an ice age happens much quicker than the beginning. But here's what's strange. The orbital forcing, the push from the Milankovitch cycles, is the same strength going into an ice age as coming out of it. The change in sunlight is symmetrical, equal but opposite. So why does the ice grow slowly but melt fast? Nobody knows for sure. Maybe it's the feedback loops. Maybe they're stronger in one direction. Maybe ice is easier to melt than to build. Maybe there's some threshold effect, some tipping point where everything accelerates. Or maybe it's about where the ice is. Ice at high latitudes near the poles is stable, cold year-round, hard to melt. But as ice spreads south, it reaches areas that are warmer, more vulnerable. When the climate shifts, the southern ice melts fast, and once it starts, the feedback loops take over. The whole system is non-linear. Small changes can have big effects. Thresholds matter, timing matters, the way different cycles interact matters. This is why the 100,000-year cycle dominates, even though it has the weakest direct effect. It's not just about the sunlight, it's about how the system responds, how the feedback loops amplify the signal, how ice and ocean and atmosphere all interact. Earth's climate isn't a simple machine. It's not like turning a dial. It's more like a pinball game. You hit the ball and it bounces around, hitting different bumpers, changing direction, building momentum. Small differences in the initial hit create huge differences in where the ball ends up. The Milankovitch cycles are the initial hit. The feedback loops are the bumpers, and ice ages are the result of the ball bouncing around the system for 100,000 years. We can see this in the data. The ice cores show it clearly. Climate doesn't change smoothly. It jumps, sudden shifts, rapid transitions, then long periods of stability. The ice builds gradually, slowly, steadily, for 90,000 years. Then suddenly, within a few thousand years, it's gone. The climate flips, temperatures jump, sea levels rise, the world transforms, and then it stays warm for 10,000 or 15,000 years, an interglacial period, like the one we're in now, stable, comfortable. Easy to forget that ice ages are the normal state, because they are. For the past million years, Earth has been in an ice age about 90% of the time. The warm periods are brief interruptions, pleasant breaks between long frozen epochs. We live in one of those breaks, the Holocene, the current interglacial. It started 11,700 years ago when the last ice age ended, and according to the orbital cycles it should be ending soon, geologically speaking. The Wobbles should be lining up to start the next ice age. Summer sunlight at high latitudes should be decreasing, snow should be accumulating, ice should be building, but it's not, because we've added something new to the system. Something the Milankovitch cycles never accounted for. Us, human civilization, industrial emissions, carbon dioxide from burning coal and oil and gas. We've increased atmospheric CO2 from 280 parts per million to over 420. In just 200 years, that's faster than any natural cycle. faster than the ocean can absorb it, faster than plants can use it. We've overwhelmed the system, and we've broken the pattern. The orbital cycles are still there, still operating, but we've added so much greenhouse gas that the cooling effect doesn't matter. Earth is warming instead. Fast. We've essentially cancelled the next ice age. At least for now. At least for the next few thousand years. Maybe longer. Whether that's good or bad depends on your perspective. Ice ages are hard. Glaciers destroy everything in their path. Sea levels drop. Climate zones shift. Entire ecosystems collapse and rebuild. But rapid warming has its own problems, different problems. Rising seas, changing weather patterns, species that can't adapt fast enough. The wobbles continue regardless, silent, slow, patient. Earth keeps tilting and spinning. The cycles keep turning. The same forces that have driven climate for millions of years. But now there's a new force in the equation, us, and nobody knows exactly how it will play out, how long our influence will last. What happens when the CO2 levels eventually drop again thousands of years from now? The ice remembers every wobble, every tilt, every shift recorded in frozen layers, a library of climate history stretching back 800,000 years, maybe more, and it's still recording, still building, still waiting to tell its story to anyone who listens. So there's a problem with the whole theory, a big problem, one that scientists noticed pretty quickly once they started looking at the actual data from ice cores and ocean sediments. The cycles don't match. Remember, Milankovitch proposed 3 cycles, the tilt cycle at 41,000 years, the wobble cycle at 23,000 years, and the orbital shape cycle at 100,000 years. But here's the thing, the orbital shape cycle is the weakest, by far. It changes the amount of sunlight reaching Earth by only about 0.1%, barely anything. The tilt cycle is much stronger, changes sunlight by about 15%. The wobble cycle is moderate, changes it by maybe 5%. So logically, you'd expect the tilt cycle to dominate. The 41,000-year rhythm should be the strongest signal in Earth's climate records, and for a while it was. Go back far enough in the ice core data, before about 1 million years ago, and you see exactly what you'd expect, a strong 41,000-year pattern. Ice ages come and go every 41,000 years, the tilt cycle is in charge. But then something changes. Around 1 million years ago, maybe a bit earlier, the pattern shifts. The 41,000-year cycle fades into the background, and the 100,000-year cycle takes over, becomes dominant, controls the rhythm of ice ages. This makes no sense. The weakest forcing somehow produces the strongest response. It's like tapping a wine glass gently with your finger and getting a huge ringing sound. While hitting it hard with a spoon produces only a quiet clink. The system is responding backwards. Scientists call this the 100,000-year problem, or sometimes the Milankovitch problem, because it suggests something is wrong with the theory, or at least incomplete. The data is clear, undeniable. For the past million years, ice ages have followed a 100,000-year cycle, almost exactly. You can see it in ice cores from Antarctica, in ocean sediments from around the world, in cave formations, in ancient beaches, 8 ice ages in the past 800,000 years, each lasting about 90,000 years, separated by warm periods of 10,000 to 15,000 years. The pattern is too regular to be random, too consistent to be coincidence. Something is pacing it, something with a 100,000-year rhythm. But the orbital eccentricity cycle, the only natural cycle at that frequency, is too weak. The math doesn't work. The forcing is tiny. The response is massive. It's like pushing a child on a swing. A small push at the right time can build up a big swing. Resonance. Timing matters more than strength. But even resonance has limits. You can't push a swing with your pinky finger and expect it to go over the bar. There has to be enough force to work with. The eccentricity cycle barely changes anything. Earth's orbit goes from slightly elliptical to slightly less elliptical. The difference in sunlight is negligible, less than the difference between a cloudy day and a clear day. Yet somehow this tiny change triggers massive ice sheets, miles thick, covering continents, lasting tens of thousands of years. Something else must be going on. Some amplification mechanism, some way the system takes a weak signal and turns it into a strong response. Scientists have been arguing about this for decades, proposing theories, testing models, trying to solve the puzzle. One idea involves the ice sheets themselves. Maybe they have their own internal rhythm, their own natural cycle that happens to match the orbital cycle. Think of it like this. Ice sheets grow until they get too big, too unstable. Then they collapse, not because of external forcing, but because of their own weight, their own dynamics. Maybe it takes about 100,000 years for an ice sheet to grow to the point where it becomes unstable, where the bottom starts melting from pressure and friction, where the whole thing begins to slide and break apart. The orbital cycles might just provide a nudge, a slight push that tips an already unstable system over the edge. The timing looks like it's controlled by the orbit, but really it's controlled by the ice. This theory has some support. Scientists know that ice sheets can collapse quickly, much faster than they grow. The end of the last ice age happened in just a few thousand years. Sudden, dramatic, like a switch flipping. But the theory has problems too. Why would the ice sheet cycle be exactly 100,000 years? That's a very specific number, and why would it sync up so perfectly with the orbital cycle? Coincidence seems unlikely. Another idea focuses on carbon dioxide. We know CO2 levels drop during ice ages, from about 280 parts per million to about 180. That's a big change, and CO2 is a powerful greenhouse gas. Maybe the carbon cycle has its own rhythm. Maybe the ocean absorbs and releases CO2 on a 100,000-year cycle. And maybe this cycle somehow links to the orbital changes. But this just moves the problem. Why would the carbon cycle operate on a 100,000-year time scale? What drives it? The weak orbital forcing still has to do a lot of heavy lifting. Some scientists think multiple cycles interact. The 100,000-year cycle doesn't work alone. It combines with the 41,000-year cycle and the 23,000-year cycle. They beat against each other, create interference patterns, amplify certain frequencies, like musical notes. Play two notes close together and you hear beats, a pulsing rhythm. The combined sound is different from either note alone. Maybe Earth's climate responds to the combined signal of all three orbital cycles, and maybe the way they combine creates a strong 100,000-year beat, even though the individual 100,000-year cycle is weak. The math for this gets complicated. You have to model how different frequencies interact, how the climate system responds to multiple inputs at once, how feedback loops amplify some signals and dampen others. Computer models can do this, and some models do produce a strong 100,000-year signal from weak orbital forcing, but the models require careful tuning, specific assumptions about how ice sheets behave, how the ocean circulates, how carbon dioxide moves between atmosphere and ocean. Change the assumptions slightly, and the 100,000-year signal disappears, or becomes too strong, or shifts to a different frequency. This makes some scientists uncomfortable. If the theory only works with very specific assumptions, maybe it's not the right theory. Maybe we're missing something fundamental. There's another weird thing about the 100,000-year cycle. It's not perfectly regular. Sometimes it's 80,000 years. sometimes 120,000 years. The average is 100,000. But there's variation. If the orbital cycle was directly controlling ice ages, you'd expect perfect regularity. The orbital cycle is like clockwork, precise, predictable. It doesn't vary, but ice ages do vary. They skip beats sometimes, or double up. The rhythm has hiccups. This suggests the climate system has some independence, some internal variability. It's not just passively responding to orbital forcing, it's doing its own thing, and the orbital cycles influence it, pace it, but don't completely control it. Imagine a drummer keeping time. Most of the time they hit the beat exactly, but sometimes they're slightly early, sometimes slightly late. They add fills, change the rhythm. The underlying tempo is still there, but there's creativity, variation. Maybe Earth's climate is like that. The orbital cycles provide the tempo, but the climate system improvises around it. Or maybe the climate system is chaotic in the mathematical sense, sensitive to tiny differences. Small changes in initial conditions create big differences in outcomes. Chaotic systems can look random, but actually be deterministic. Follow rules. But the rules are so sensitive that prediction becomes impossible, like weather. We can forecast a few days ahead, but not weeks or months. The system is too chaotic. Maybe ice ages are chaotic too. The orbital cycles provide some structure, some predictability, but chaos adds noise, variation, makes each ice age slightly different. This would explain why the pattern isn't perfect, why ice ages sometimes come early or late, why the 100,000-year rhythm has wobbles, but it makes the problem harder to solve. Because chaos means we can't predict exactly, can't say for certain what causes what, can only talk about probabilities, tendencies, rough patterns. Some scientists think we're asking the wrong question. Maybe there isn't one cause, one mechanism, one explanation. Maybe ice ages result from multiple factors, all working together, sometimes reinforcing each other, sometimes cancelling out. The system is too complex for simple answers. The orbital cycles matter, the feedback loops matter, the ice sheet dynamics matter, the carbon cycle matters, ocean circulation matters, even random chance matters. All of these things interact, create a complex system, and the 100,000-year pattern emerges from that complexity. Not because of one dominant cause, but because of how everything fits together. This is unsatisfying in a way. Scientists like clean explanations, simple theories, elegant solutions. Complexity feels messy, hard to test, hard to prove, but maybe that's just how Earth works. Maybe climate is inherently complex, multiple causes, multiple feedbacks, no single answer. The ice cores keep providing data, more detail, better resolution. Scientists can now see changes that happened over decades, sometimes years. The records are incredibly precise, and the more precise the data gets, the more complicated the picture becomes. There are cycles within cycles, sudden jumps, gradual trends, regional differences, global patterns. Every answer raises new questions. Every solution reveals new problems. Why did the 100,000-year cycle start 1 million years ago? What changed? Before that, the 41,000-year cycle dominated. What flipped the switch? Some scientists think ice sheets got bigger. Before 1 million years ago, ice ages were smaller. Ice didn't spread as far south, didn't get as thick, didn't last as long. Maybe once ice sheets reached a certain size, they started behaving differently, became more stable, harder to melt, took longer to build and collapse. And this changed the system's natural frequency from 41,000 years to 100,000 years. But why did ice sheets get bigger? What allowed them to grow larger than before? Maybe Earth cooled slightly, a long-term cooling trend over millions of years. As Earth cooled, ice could survive farther south, build thicker, last longer. Or maybe ocean circulation changed, the way currents move heat around the planet. A small change in circulation could allow ice to accumulate differently. Or maybe mountain ranges rose higher. The Himalayas, the Rockies. Higher mountains mean more area above the snow line, more places where ice can start growing. All of these things probably played a role, slowly, gradually, over millions of years, until the system crossed some threshold and the rhythm changed. The 100,000-year problem remains unsolved, not because scientists aren't smart enough or don't have enough data, but because the system is genuinely complex, multiple causes, multiple effects. No single explanation captures everything. And maybe that's okay. Maybe some questions don't have simple answers. Maybe the universe is messy, complicated, full of interactions we're still figuring out. The ice remembers it all. Every cycle, every wobble, every shift, locked in frozen layers, waiting to tell its story. We can read that story now, extract the data, build the graphs, see the patterns, but understanding why the patterns exist, that's harder. That takes time, more research, more thinking. The 100,000-year problem isn't solved, but we're getting closer. Each study adds a piece. Each model refines our understanding. Each ice core reveals new details. And in the meantime, the cycles continue. Silent, patient, indifferent to our confusion. Earth keeps wobbling, keeps tilting, keeps moving through space. The ice keeps recording, keeps building, keeps waiting. So what actually drives ice ages? We've got the orbital cycles, the wobble, the tilt, the stretch. We know they matter. The timing lines up too well to be coincidence. But we also know they're not enough. The forcing is too weak. Especially that 100,000-year cycle. It barely changes anything, yet somehow it controls the whole show. Something takes that weak signal and amplifies it. Turns a whisper into a roar. But what? The answer might be ice itself. Ice sheets don't just sit there. They are not passive. They don't just grow when it's cold and melt when it's warm. They have their own behavior, their own dynamics, their own way of changing the world around them. Think about what happens when an ice sheet forms. Snow falls in northern Canada, in Scandinavia, on Greenland. Year after year, the snow piles up, compresses, turns to ice. At first it's just thick, a layer of ice covering the ground, maybe a few 100 feet. That's not enough to change much, but it keeps growing. The ice gets thicker, heavier, starts flowing under its own weight, spreading outward, moving south. And here's where things get interesting. Ice is white, bright white. It reflects sunlight. About 80% of the sun's energy bounces right back into space. Dark ground absorbs sunlight. About 80% gets absorbed, turned into heat. But ice reflects it, sends it away. The ground stays cold. This creates a feedback loop. More ice means more reflection. More reflection means less heat. Less heat means more ice can survive, which means more reflection. The cycle feeds itself. Scientists call this the ice albedo feedback. Albedo means reflectivity. Ice has high albedo. Dark ground has low albedo. The difference matters a lot. Once an ice sheet reaches a certain size, it starts creating its own climate, making its own weather. The bright surface reflects heat. The cold air above the ice sinks, flows outward, pushes warm air away. The ice sheet becomes self-sustaining. It doesn't need the orbital cycles anymore. It makes its own cold. But there's more. Ice sheets change the land underneath them. Their weight is enormous. A mile of ice weighs about 900 tons per square meter. That's like parking 600 cars on every square meter of ground. The Earth's crust can't support that weight. It bends, sinks, slowly, over thousands of years. The land under the ice sheet drops, sometimes by hundreds of feet. This matters because of how ice sheets grow. They need altitude, cold temperatures, snow that doesn't melt in summer. When the land sinks, the ice surface sinks too. Lower altitude means warmer temperatures, even just a few degrees warmer. That makes the ice more vulnerable, more likely to melt. So ice sheets create their own problem. They grow big, get heavy, push the land down, lower their own elevation, make themselves easier to melt. This might explain the timing, why ice ages last so long, why they end relatively quickly. The ice sheet grows for tens of thousands of years, gets thicker, spreads farther. The land underneath slowly sinks. The whole system becomes more and more unstable. Then something tips it over. Maybe the orbital cycles provide a nudge, a bit more summer sun, a bit warmer temperatures, just enough. The ice starts melting, not everywhere, just at the edges, just a little. But that little bit matters, because ice sheets have another property. They insulate the ground underneath them. The bottom of an ice sheet isn't at air temperature, it's warmer, sometimes close to freezing, sometimes actually melting. The pressure helps. A mile of ice creates enormous pressure. Pressure lowers the melting point. Ice can melt at temperatures below 32 degrees Fahrenheit, so the bottom of the ice sheet is wet, slippery. And when the ice sheet starts losing mass at the edges, the whole thing can start sliding, moving faster, breaking apart. This is how ice sheets collapse, not by melting in place, that would take forever, but by sliding into the ocean, breaking into icebergs, floating away. The collapse can be fast. Geologically speaking, a few thousand years, maybe less. The ice that took 90,000 years to build disappears in 10,000, and once it starts collapsing, the feedbacks reverse. Less ice means less reflection, more dark ground exposed, more sunlight absorbed, more heat, more melting. This cycle feeds itself again, but in the opposite direction. This explains a lot. Why ice ages last so long, why they end quickly, why the system seems to have two stable states, glacial and interglacial, cold and warm, with rapid transitions between them. But it still doesn't fully explain the 100,000-year rhythm. Why do ice sheets take about 100,000 years to reach the tipping point? Why not 50,000? Why not 200,000? The answer might involve multiple factors. Ice sheet dynamics, orbital cycles, carbon dioxide, ocean circulation, all working together. Carbon dioxide drops during ice ages. We know this from ice cores. The bubbles trapped in ancient ice show it clearly. About 280 parts per million during warm periods. About 180 during ice ages. That's a big drop. And CO2 is a greenhouse gas. Less CO2 means less heat trapped, cooler temperatures, more ice. But why does CO2 drop? What causes it? The ocean. The ocean holds about 50 times more carbon than the atmosphere. It's a giant reservoir. Carbon moves between ocean and air constantly, dissolving in, bubbling out. The balance shifts. Cold water holds more CO2 than warm water, like a cold soda. It stays fizzy. Warm it up and the gas escapes. During ice ages, the ocean gets colder, especially in polar regions. Cold water sinks, takes dissolved CO2 with it, down to the deep ocean, where it stays, locked away for thousands of years. Less CO2 in the atmosphere means cooler temperatures, which means more ice, which means more reflection, which means even cooler temperatures. Another feedback loop, but there's more to it. Ocean circulation matters. The way currents move heat around the planet, the conveyor belt of water flowing from equator to poles and back. During ice ages, this circulation changes, slows down, maybe even stops in some regions. Fresh water from melting ice dilutes the salt in the ocean, changes its density, disrupts the flow. When circulation slows, heat doesn't move as efficiently. The poles get colder, the tropics might get warmer, the whole climate system reorganizes. These circulation changes might trigger rapid shifts, sudden cooling, sudden warming. The climate doesn't change smoothly, it jumps, flips from one state to another. Scientists see this in the ice core records. Temperature doesn't rise gradually, it jumps, sometimes by 10 degrees in just a few decades, then stays stable for centuries, then jumps again. These rapid changes suggest the climate system has thresholds, tipping points. Push it far enough and it flips to a different state, like a light switch, not a dimmer. Ice sheets might have their own tipping points. Grow them to a certain size and they become stable, hard to melt. Shrink them below a threshold and they collapse quickly. The orbital cycles might push the system toward these thresholds, slowly, over thousands of years. Then one summer is just warm enough. One winter doesn't add quite enough snow. The ice sheet crosses the threshold, starts collapsing. The timing looks like it's controlled by the orbits, and in a way it is, but the orbits are just providing the pacing, the push. The system's own dynamics do the rest. This is called a forced oscillation with internal amplification. The external force is weak, but the system responds strongly because of its own properties, its own feedbacks, its own instabilities. It's like pushing someone on a swing. You don't have to push hard, just at the right time. The swing does most of the work, its own momentum, its own rhythm. You just keep it going. Earth's climate might work the same way. The orbital cycles are the push, small, regular, predictable. But the climate system has its own natural rhythm, its own tendency to oscillate between glacial and interglacial states. The orbital cycles keep that oscillation going, provide the timing. But the amplitude comes from the system itself, the feedbacks, the ice, the carbon, the ocean, all amplifying the signal. This explains why the 100,000-year cycle dominates even though the forcing is weak. The system is tuned to respond at that frequency. Like a radio tuned to a specific station, it picks up that signal and amplifies it. But why is the system tuned to 100,000 years? Why not some other frequency? That's still unclear. It might have to do with how long it takes ice sheets to grow to critical size, how long it takes the land to sink enough, how long it takes carbon to move between atmosphere and ocean. All of these processes have timescales. None of them are instant. They take thousands of years, maybe tens of thousands. And when you combine them all, the natural timescale of the system comes out to about 100,000 years. Or maybe it's simpler. Maybe the 100,000-year orbital cycle, even though weak, is just persistent enough to pace the system. It keeps pushing at the same frequency, never stops, never varies, and over time the system syncs up with it, like a metronome. Tick, tick, tick. Keep it going long enough and everything starts moving to that beat. The ice cores show this synchronization. The timing is too regular to be random. 8 ice ages in the past 800,000 years, each lasting about 90,000 years, each ending in about 10,000 years. The pattern repeats, but it's not perfect. There's variation. Some ice ages last 80,000 years, some last 120,000. The interglacials vary too. Some are longer, some shorter. The current one is already 11,700 years old, longer than average. This variation suggests the system isn't completely controlled by the orbital cycles. There's some independence, some chaos, some randomness. Maybe it's like a ball rolling in a bowl. The bowl has a shape. The ball tends to roll. toward the bottom. But exactly where it goes depends on how you push it, how fast, what angle. Small differences matter. The orbital cycles are like gentle pushes. They influence where the ball goes, but they don't control it completely. The ball has its own momentum, its own path. Earth's climate is the ball, the feedbacks are the bowl, the orbital cycles are the pushes. The result is a pattern, mostly regular, but with variation, with unpredictability. This makes prediction hard. We can see the pattern in the past, but can we predict the future? When will the next ice age start? How long will this warm period last? The orbital cycles tell us something. Right now, the cycles are in a configuration that should favour warmth. The next ice age shouldn't start for tens of thousands of years, maybe 50,000, maybe more. But that's based on the orbital cycles alone. It assumes the system responds the same way it has in the past. It doesn't account for what humans are doing, the CO2 we're adding, the way we're changing the system. We're running an experiment, adding greenhouse gases faster than the natural cycles ever did, pushing the system in ways it hasn't been pushed before. The result is uncertain, but that's a different story, a different question. Right now we're asking about the natural cycles, the rhythm Earth has followed for millions of years. Before humans, before civilization, before we learned to burn fossil fuels and change the atmosphere. The natural rhythm is ice, long periods of cold, brief periods of warmth, driven by wobbles in Earth's orbit, amplified by ice sheets, by carbon, by ocean currents, by feedbacks we're still figuring out. It's a complex system, multiple causes, multiple effects, but the pattern is clear. Regular, persistent, Earth freezes, Earth thaws, over and over, following a beat set by the sky. Carbon dioxide. It sounds so simple, just a gas in the air, but it's one of the most important players in this whole story when we talk about the cycles of ice and warmth, about Earth freezing and thawing. Carbon dioxide is always there in the background, quiet, invisible, but powerful. Let's try to see how it really works. Not just the big picture, but the details. How do we know carbon dioxide acts as an amplifier for ice ages? What is the actual evidence? And why does it matter so much? First, think about what we actually see in the records. Ice cores from Antarctica and Greenland are like time machines. Scientists drill down more than 2 miles through the ice. Each layer is a year or two of snowfall, pressed into a thin sheet. As the snow fell, it trapped tiny bubbles of air. Those bubbles are still there. Ancient air, frozen for hundreds of thousands of years. When scientists pull out an ice core, they can actually measure the air from, say, 20,000 years ago. They look for carbon dioxide in those bubbles. Turns out there's a clear pattern. Every time the planet was cold, an ice age, the carbon dioxide in the air was low, about 180 parts per million. Every time the planet warmed up, the CO2 rose, back up to about 280 parts per million. It's not just a coincidence. The rises and falls match up almost exactly with the timing of the ice ages. The coldest times always have the lowest CO2. The warmest times have the highest. The lines on the graph move together like two dancers locked in step. Now, here's where it gets interesting. The CO2 changes don't just follow the temperature. Sometimes the CO2 starts changing before the big warming kicks in. Sometimes it lags a bit. But the two are always linked. When CO2 increases, the planet warms. When it drops, the planet cools. It's a partnership. How do we know CO2 is actually causing the change and not just tagging along? That's a fair question. People used to argue about it. But now the evidence is strong. Think about how greenhouse gases work. Carbon dioxide isn't the only one, but it's the most important for these timescales. Sunlight hits the Earth. The surface absorbs the energy. Most of it is re-radiated back out as heat, as infrared light. Greenhouse gases like CO2 trap some of that heat. They let sunlight in but slow the escape of warmth. It's like putting on a thin blanket. If there's more CO2 in the air, more heat stays in. If there's less, the planet loses heat faster. This isn't a theory, it's basic physics. We can measure it in the lab. We can see it on other planets too. Venus is hot not because it's closer to the Sun, but because its atmosphere is full of carbon dioxide. So, when the ice cores show that CO2 drops during ice ages, it means Earth's blanket gets thinner. More heat escapes. The planet cools, and the ice sheets can grow. When CO2 rises, the blanket thickens. Earth holds onto more warmth. The ice sheets melt. But how much does CO2 really matter? Is it just a small helper, or is it a big amplifier? Here's what the numbers say. During an ice age, the difference in CO2 is about 100 parts per million, 180 in an ice age, 280 in a warm period. That 100 ppm change is enough to shift global temperatures by about 4 to 6 degrees Celsius. That's 7 to 11 degrees Fahrenheit. It's a big swing, enough to turn Canada into a frozen wasteland, or a green forest, enough to cover New York City in a mile of ice, or fill it with trees and rivers. The fact that CO2 changes line up so closely with temperature is a big clue. But there's more. Scientists can compare the timing in detail. When the planet starts to warm at the end of an ice age, the first thing that happens is a small increase in sunlight at high northern latitudes. That's the orbital cycles at work. Not much extra energy, but just enough to start melting the edge of the ice. Then, a little later, the CO2 starts to rise. It's not instant. It takes a few hundred years. But as CO2 rises, the warming speeds up. The ice melts faster. The planet shifts from cold to warm in just a few thousand years. It's like starting a fire. The orbital cycles are the spark, but CO2 is the fuel. Once the fire is going, it burns hot and fast. Without that fuel, the spark wouldn't be enough. Scientists have tried to model this with computers. They take the orbital changes alone and ask the model what happens. The answer is clear. You get some warming, but not enough to explain the real record. Add in CO2 changes, and the model matches the ice core data almost perfectly. The temperature swings make sense, the timing works out, the evidence comes together. There's another way to see the power of CO2. Look at the numbers. The direct effect of changing CO2 from 180 to 280 ppm is about 2 degrees Celsius of warming, just from the greenhouse effect. But that's only half the story. When the planet warms, other feedbacks kick in. The ice melts. That changes the reflection of sunlight, as we saw earlier. More dark ground, more heat absorbed. The oceans warm up and release more CO2. The atmosphere holds more water vapour, which is another greenhouse gas. All these feedbacks add up. The total warming is about double what you'd expect from CO2 alone. So CO2 acts as both a driver and an amplifier. It starts the process and then helps push it further. The system feeds on itself. A little warming releases CO2, which causes more warming, which releases more CO2. The cycle continues until something stops it. But where does all this CO2 come from, and where does it go? That's where the ocean comes in. The ocean is the real giant in this story. It holds about 50 times more carbon than the air. Most of it is dissolved, like sugar in tea. Some of it is in the deep ocean, some near the surface. The balance between these places is always changing, but slowly. During ice ages, the oceans are colder. Cold water can hold more CO2, just like a cold soda holds more fizz. So when the planet cools, the oceans soak up more carbon from the air. The CO2 Level in the atmosphere drops. That helps the planet cool even more, but when the planet starts to warm, the oceans warm too. Warm water can't hold as much CO2. The gas bubbles out, escapes to the air, the CO2 level rises, the planet warms further. This is another feedback loop. There are other ways carbon moves between air and sea. Tiny plankton in the ocean use CO2 to build their bodies. When they die, some of their remains sink to the bottom, taking carbon with them. Ocean currents stir the deep and surface waters, bringing up old carbon or sending new carbon down. The winds over the ocean can even change how much CO2 bubbles out. During ice ages, the ocean currents and winds are different. The whole system slows down. Less mixing means more CO2 stays trapped in the deep ocean. When the ice age ends, the system speeds up. The deep ocean releases its carbon. The air fills up with CO2 again. Scientists have looked for evidence of these changes. They've studied ocean sediments, layers of mud at the bottom of the sea. These layers hold tiny shells from plankton, and each shell has a record of the water's chemistry. By measuring the carbon in these shells, scientists can see when the deep ocean was storing more CO2 and when it was releasing it. The results match up with the ice core data. During the coldest parts of the ice ages, the shells show the deep ocean was full of CO2. The atmosphere was low in CO2. When the planet warmed, the deep ocean released its carbon, and the air filled up again. There are even clues from the land. During ice ages, giant dust storms swept across the continents. The ice sheets ground up rocks, making huge clouds of fine dust. Some of that dust blew out over the oceans, especially the Southern Ocean near Antarctica. This dust carried iron, which is a key nutrient for plankton. When the dust fell into the sea, the plankton bloomed. They pulled extra CO2 out of the air, helping to lower the atmospheric carbon even more. When the ice age ended, the dust storms faded. Less iron, fewer blooms, less CO2 pulled out of the air. So carbon dioxide is pulled in many directions at once. The ocean, the land, the winds, the plankton, each piece matters, but the overall pattern is clear. Cold times mean low CO2. Warm times mean high CO2, and the swings are big enough to change the whole climate. Some people wonder if the changes in CO2 are just a side effect. Maybe the warming causes the carbon to rise, not the other way around. But experiments and models say otherwise. If you fix CO2 at ice age levels, the planet stays cold, even if the sunlight increases. If you add CO2, the planet warms fast, even if sunlight doesn't change much. The effect is real, and it's strong. You can even see it in the speed of the transitions. At the end of each ice age, the warming is fast, just a few thousand years. That matches the speed of CO2 rising in the ice cores. When CO2 jumps up, the planet follows. The ice melts. The forests return. Animals and people expand into new lands. If CO2 didn't matter, the change would be slower. The small increase in sunlight from the orbital cycles isn't enough to explain the quick jump. But with CO2 rising, the planet has a booster, a turbo button. That's why the change can be so sudden. So the evidence for CO2 as an amplifier is strong. The ice cores show the timing. The ocean sediments show the storage and release. The models show the effect on temperature. The details match up. But there are still open questions. For example, why does CO2 drop so much during ice ages? Why does the system shift between storing carbon in the ocean and releasing it? What causes the deep ocean to lock up so much CO2 for tens of thousands of years, then suddenly let it go? Some scientists think it's all about the way the ocean circulates. During ice ages, the winds and currents change. The deep water gets more isolated from the surface. Less mixing means more. Carbon gets trapped. When the planet warms, the ice melts, the winds shift, the mixing increases. The deep ocean releases its carbon. Others point to the plankton. Maybe the giant dust storms during ice ages supercharged the plankton, letting them pull more CO2 out of the air. When the dust faded, the plankton slowed down and the CO2 went back up. There's even a role for the land. During ice ages, forests shrink, deserts grow, soil carbon changes. All of these things move carbon from one place to another. But the biggest player is still the ocean. Scientists are still working out the details. They build better models, look for new clues, drill deeper ice cores, collect more ocean mud. But the big picture is clear. CO2 is the main amplifier. It doesn't start the ice ages, but it makes them much more dramatic. It turns small changes in sunlight into giant changes in climate. It's the reason why the planet can swing from Sahara-like deserts to frozen tundra and back again. And the numbers are huge. During an ice age, about 10 million square miles of land are covered in ice. When the CO2 rises, most of that ice melts away. Sea levels rise by over 400 feet. Coastlines move, rivers change course, ecosystems shift overnight, at least in geological terms. We see the effect everywhere, in the fossils of plants and animals, in layers of pollen in lake beds, in ancient soils buried under old ice. The story is always the same. When CO2 is low, life retreats. When CO2 rises, life floods back in. That's why scientists pay so much attention to CO2. It might be invisible, but it's not silent. It leaves its mark on the whole planet, and once you start looking for it, you see it everywhere. Here's something else to think about. The amount of CO2 in the air during these cycles is tiny compared to all the carbon in the ocean and rocks. But even small changes in the air make a huge difference. The planet is sensitive. The climate system is balanced on a knife edge. It doesn't take much to tip it one way or the other. A slow shift in CO2, a small change in sunlight, a change in ocean currents. The feedbacks do the rest. And that's why the ice ages are so regular but also unpredictable. The orbital cycles set the timing, but CO2 sets the volume. The music plays, but the loudness changes. Sometimes it's a whisper, sometimes a roar. We can even see the CO2 amplifier working today. Since the Industrial Revolution, humans have added about 130 parts per million of CO2 to the air. That's more than the difference between an ice age and a warm period. The result is a planet that's warming faster than at any time in the last 10,000 years. But that's another story. Right now we're talking about the natural cycles, the way the planet has moved between ice and warmth for millions of years. The CO2 amplifier has always been there, sometimes quiet, sometimes loud, but always in the background. It's a reminder that the planet isn't just shaped by rocks or ice or sunlight. It's shaped by invisible things too. Tiny molecules in the air, bubbles trapped in ice, gases dissolved in the sea, all connected, all playing a part. When you look at the big picture, you see a system that's both fragile and strong. It can flip from one state to another, given the right nudge, but it always finds a new balance, a new rhythm. CO2 is part of that rhythm, not the only part, but one of the most important. It's the amplifier that turns small changes into big ones, the reason why the planet can change so much and so quickly, and the evidence is all around us, in the ice, in the ocean, in the land, in the stories told by ancient air and old mud and fossil forests. So next time you hear about carbon dioxide, remember it's not just a number or a gas or something in the news. It's one of the main reasons why Earth freezes and thaws over and over for millions of years. But CO2 isn't the only amplifier. The oceans themselves play a huge role too. Their currents, their hidden heat, their deep secrets. And when they change, everything changes. The ocean is a world all its own. It's not just a big pool of water, it's layered, moving, and always shifting in ways that are hard to see from the surface. If you could slice the ocean open, you'd see something like a giant sandwich. Warm water on top, colder water below, and the deepest layers far beneath that. Each layer holds different amounts of heat and carbon, and how those layers mix and move changes everything for the planet. Let's start with what's actually happening down there. The ocean isn't still. Currents flow across the surface, sometimes for thousands of miles. The Gulf Stream, for example, brings warm water from the Gulf of Mexico all the way across the Atlantic to Europe. That's why winters in London aren't nearly as cold as winters in Quebec, even though both places are about the same distance from the North Pole. Ocean currents carry heat. They act like conveyor belts, moving warmth from one part of the globe to another. But the real action is deeper down. Think about the great conveyor belt of the ocean. Scientists call it the thermohaline circulation. That just means it's driven by temperature and salt. Here's how it works. In the far north, near Greenland, the surface water gets very cold. Sometimes it even freezes to form sea ice. When that happens, salt gets left behind in the water. This makes the water heavier and saltier, so it sinks. This cold, salty water then flows south along the bottom of the Atlantic, slipping beneath the warmer water above. At the same time, in the Southern Ocean near Antarctica, a similar thing happens. Cold, salty water sinks and spreads north along the ocean floor. It can take hundreds or even thousands of years for a drop of water to complete this loop around the globe. This slow, deep movement is how the ocean stores and releases heat. It also locks away carbon. When surface water sinks, it carries carbon with it, trapping it deep below. When deep water comes back up, it can let that carbon out again. So, what's the evidence that this circulation matters for ice ages? Scientists have looked for clues in the mud at the bottom of the ocean. Every year, tiny shells, bits of dust and other debris settle down to the sea floor. Over time, these layers build up like pages in a diary. By drilling into the mud, scientists can pull up long cores, samples that give a record going back hundreds of thousands of years. Inside these cores are clues about the past. Some are chemical, like the amount of carbon in the shells of tiny plankton. Others are physical, like the size and shape of the shells, which can tell you about the temperature of the water when they lived. One of the best-known examples comes from the Atlantic Ocean. During the last ice age, the deep Atlantic was different from today. It was colder, and the water was more isolated from the surface. Scientists can tell because the chemical fingerprints in the shells show a build-up of carbon in the deep sea. Less carbon was making its way up to the surface and into the air. Why would this happen? During ice ages, the winds and currents shift. The ocean lid gets tighter, less mixing between surface and deep water. The conveyor belt slows down. Cold, salty water still sinks, but it doesn't pull as much surface water down with it. The deep ocean becomes a carbon trap. Then, as the planet starts to warm, the system wakes up. The currents get stronger. More mixing happens between the deep and the surface. Carbon that was locked away deep underwater starts to leak out, rising up and escaping to the air. That's one reason why CO2 rises as the ice age ends. It's not just the land or the air changing, it's the ocean releasing its stored carbon. Let's look at a real example. In the Southern Ocean around Antarctica, there's a special place where deep ocean water comes up to the surface. This is called upwelling. It's like a slow-motion fountain, bringing cold, carbon-rich water up from the bottom. Today, this upwelling brings nutrients that feed massive blooms of plankton. But during the Ice Ages, things were different. Evidence from seafloor cores shows that during the coldest times there was less upwelling. The wind patterns changed, and the water didn't rise as much. That meant less carbon made its way from the deep to the surface, and less escaped to the air. The result? The atmosphere had lower CO2, helping the planet to stay cold. But as the ice started to retreat, the winds shifted again. Upwelling increased, bringing more deep water and its trapped carbon up to the surface. More CO2 bubbled out and filled the air. The planet warmed even faster. This isn't just a guess. Scientists can see the timing in the mud. The types of plankton change. The chemistry in the shell shifts. The layers show a pulse of carbon coming out of the deep ocean right when the planet is warming up. The match is almost perfect. Now let's talk about how heat moves in the ocean. The ocean holds far more heat than the air. In fact, the top 10 feet of the ocean holds as much heat as the entire atmosphere above it. When the ocean takes in extra heat, it doesn't warm up right away. It absorbs the energy, mixes it around, and slowly releases it over time. During ice ages, much of the ocean's heat is locked up at the surface, covered by thick ice in the far north and south. The deeper parts stay cold and dark. But as the ice melts, the sun can warm a bigger area. The surface heats up and more of that warmth can mix down into the depths. This mixing isn't even. It depends on wind, storms, and how salty the water is. Sometimes a shift in wind patterns can push warm water down deeper, spreading heat through the ocean. Other times the ocean can trap cold water under a layer of warm water, keeping the surface mild even while the depths stay chilly. A good example comes from the North Atlantic. Today, when the Gulf Stream slows down, Europe can get cooler winters. If the whole conveyor belt system changed, it could shift the climate much more. During ice ages, evidence shows the conveyor belt was weaker. That trapped more cold water in the deep ocean and helped the ice sheets grow. Scientists have even found hints of sudden events, moments when the ocean currents changed quickly. In some ice cores and seafloor records, you can see signs of abrupt warming or cooling that happened over just a few decades. These climate jumps may have been caused by big changes in ocean circulation. For example, a sudden rush of fresh water from melting ice could have shut down the conveyor belt. That would have left heat building up in the tropics while the north stayed cold. Let's get concrete. Around 12,800 years ago, the world was warming up after the last ice age. But suddenly the North Atlantic cooled sharply for about 1,000 years. This period is called the Younger Dryas. What happened? The evidence points to a large flood of fresh water pouring into the North Atlantic from melting ice sheets. This fresh water stopped the formation of cold, salty water that usually sinks and drives the conveyor. With the engine stalled, heat couldn't move north as easily. The result, Europe and parts of North America got much colder, almost like the Ice Age had returned. Then, just as suddenly, the system restarted. The conveyor belt picked up again. Warm water rushed north, and the planet finished thawing out. The whole world shifted into the warmer climate we've had ever since. The ocean isn't just a background player. It's the memory of the climate system. It stores heat for centuries, even millennia. It soaks up carbon and hides it away, only to let it out again when currents shift. The evidence for all this comes from many places: ice cores, seafloor mud, the chemistry of tiny shells, and even the ancient coastlines that show where sea levels used to be. There's more. During ice ages, sea level drops by more than 400 feet because so much water is locked up in ice sheets. This exposes huge areas of the sea floor, changing the shape of the continents. The shallow seas disappear. The edges of the ocean move far out from where they are now. This affects the way heat moves around the planet too. The new coastlines change wind patterns, ocean currents, and the way the sun's energy is absorbed. When the ice melts and sea levels rise, the shallow seas flood back in. New currents form. The whole system gets a fresh start. The evidence shows that these changes in ocean shape and depth play a role in the start and end of ice ages. Let's not forget the role of life in the ocean. Tiny plankton float near the surface, using sunlight to grow. They take in carbon from the water. When they die, some sink to the deep ocean, carrying carbon with them. This is sometimes called the biological pump. During ice ages, there are signs that this pump ran faster. More plankton grew, more sank, and more carbon was locked away in the depths. How do we know? Scientists look at the types of fossils and the chemistry in their shells. They can tell when plankton blooms were bigger. These blooms are often helped by dust blowing off the land, carrying nutrients like iron into the sea. We talked about this before, but here's something new. The strength of the biological pump is tightly linked to ocean circulation. When the deep ocean is more isolated, the pump works harder because nutrients stay near the surface longer. But when the currents start moving again, deep water rises and brings up nutrients from below. The pump slows down and more carbon escapes back to the air. It's a delicate balance. The ocean's life and its circulation are tied together. All of this matters because the ocean sets the pace of climate change. The air can warm up or cool down in only a few years, but the ocean takes centuries to fully respond. That's why the end of an ice age isn't just a smooth, steady thaw. Sometimes it's a stop-and-go process. Warm years, then sudden freezes, then back to warming again. The clues are everywhere if you know where to look. In the North Pacific, scientists found layers of mud that show sudden jumps in plankton growth, matching times when the ocean currents changed. In the Indian Ocean, cores show shifts in salt and temperature that line up with big changes in the ice sheets. Even in the deepest parts of the Atlantic, there are chemical traces that show when the deep water was filled with carbon and when it was released. The big picture is this. The ocean isn't just a passive water tank. It's an active player in the Earth's climate. Its currents move heat and carbon around the globe. When those currents change, the whole climate can shift, sometimes very quickly. Let's step back for a second. Why does the ocean circulation change in the first place? The answer usually starts with small triggers, like changes in Earth's orbit, which shift where sunlight falls. That can start melting ice at the edges. The fresh water from melting ice pours into the sea, making the surface less salty. That can slow down the sinking of cold water, which slows the conveyor belt. Less heat moves north, and the ice grows back. Or, if the system tips the other way, the conveyor speeds up, bringing warm water north, melting the ice and raising temperatures. It's a system full of feedbacks. Each piece pulls on the others. If the conveyor slows, the north gets colder, ice grows, and the ocean stores more carbon. If it speeds up, the north warms, ice melts, and carbon is released. And here's something even stranger. Even small changes in the ocean can have big effects. A shift in wind over the Southern Ocean, for example, can change the amount of deep water that rises, which can add or remove a lot of carbon from the air. That, in turn, changes how much heat the planet holds. It's all connected. There's also evidence from coral reefs. Some ancient corals buried in what are now dry islands grew at times when sea level was higher. Others stopped growing when sea level fell during ice ages. By dating these corals, scientists can track how fast sea level changed and how quickly ice melted. The speed of these changes matches the timing of shifts in ocean currents and carbon release. The ocean's story is written in all these places: mud, shells, coral, chemistry, ancient coastlines. Each one gives a piece of the puzzle. When you put them together, you see a giant system, always in motion, always changing. Another clue comes from the Arctic Ocean. During ice ages, the sea ice there was much thicker and lasted all year. That made it even harder for deep water to form and sink. When the ice melted, the conveyor could start again. The timing of these changes matches up with big jumps in CO2 and temperature seen in the ice cores. Let's not forget how the ocean connects the whole planet. Warm currents flow from the tropics to the poles. Cold currents return along the bottom. When the system is working, heat spreads across the globe. When it stalls, some places freeze while others bake. The ocean also acts as a buffer. When the air warms, the ocean soaks up some of that extra heat, slowing the warming on land. But there's a limit. If the ocean gets too warm, it can't absorb as much heat or carbon. Then climate changes can speed up. So, all the evidence points in the same direction. The ocean's circulation, its great currents and deep mixing, controls how much heat and carbon the planet can hold. When those currents slow or stop, the planet cools and the ice grows. When they speed up, the planet warms and the ice melts. And the really wild part? These changes can happen quickly, at least in geological terms. Sometimes the climate flips in just a few decades. Sometimes it lingers in one state for thousands of years. But it's always the ocean, quietly working in the background, that makes these swings possible. You can think of the ocean as Earth's slow heartbeat. Each pulse sends heat and carbon around the world. When the rhythm changes, so does the climate. The ice ages are not just about cold air and frozen land. They're about deep water, hidden currents, and the way the ocean remembers. So, when you look at the history of Earth freezing every 100,000 years, you see the ocean at the center. It's the giant player that sets the stage for everything else. The evidence is there, in the mud, in the shells, in the ice, in the rocks. All of it points to the same story. The ocean moves, and the world changes. And while CO2 is the amplifier, the ocean is the stage and the engine. It stores the heat, it locks up the carbon, it decides when to release both. And when it does, the planet can swing from deep freeze to warm green world and back again. All these pieces, ocean currents, deep water, heat, carbon, plankton, ice, work together. They make the system tick. But here's the mystery. Even with all this evidence, scientists are still trying to figure out exactly why the timing is so regular. Why does the planet flip from ice to warmth every 100,000 years, almost like clockwork? That's the next big puzzle, and it's what we'll look at next. So we've talked about the ocean's role and how it moves heat and carbon around. But even with all that, there's a question hanging in the air. Why is the timing of ice ages so regular? Why does Earth freeze and thaw every 100,000 years, almost like clockwork? It's not random. Something is setting the pace. This is where things get a bit weird, and honestly, kind of fascinating. Scientists have been trying to solve this puzzle for decades. They've looked at every clue they can find. Drilled ice cores from Antarctica, pulled mud from the bottom of the sea, counted layers in cave rocks. All these clues show the same thing. The ice ages come and go on a steady beat, about every 100,000 years. But here's the catch. The changes in Earth's orbit, the so-called Milankovitch cycles, don't line up perfectly with this 100,000-year rhythm. Earth's orbit does get more or less stretched out over time. Sometimes it's more like a circle, sometimes more like an oval. This change, called eccentricity, happens in cycles of about 100,000 years. So you might think, okay, that explains it. But when you look closer, it doesn't quite add up. The effect of this orbital stretching on sunlight is actually pretty weak. It only changes the amount of sunlight Earth gets by a tiny bit, not nearly enough to freeze the planet or melt the ice sheets. For a long time, scientists thought there must be something else going on, something that takes these small regular nudges from Earth's orbit and turns them into huge swings between ice and warmth. This is where a strange idea comes in, something called stochastic resonance. The name sounds complicated, but the idea is simple once you break it down. It's about noise. And by noise, scientists don't mean just sound. They mean any random, unpredictable change in the system. A little bit of chaos, a bit of background static. Let's use an example. Imagine you're trying to push a kid on a swing, but instead of standing behind them, you're standing off to the side. You give tiny, regular pushes, but they're not lined up perfectly with the swing's motion. The swing barely moves. Now, imagine there's a gusty wind blowing, sometimes strong, sometimes weak. Most of the time, the wind just makes things a bit wobbly, but every once in a while, the wind and your push line up just right. Suddenly, the swing soars much higher. That's stochastic resonance. The small, regular push by itself isn't enough. The random gusts by themselves aren't enough. But together, they can make something big happen. The system resonates. It picks up energy from both the regular push and the random noise, and suddenly you get a big swing. Now picture Earth's climate as that swing. The regular pushes are from Earth's orbit, very slight changes in sunlight, happening on a steady schedule. The noise comes from lots of places: volcanic eruptions, changes in ocean currents, maybe even things like dust storms or shifts in the way plants grow. Each one is random, sometimes big, sometimes small, sometimes nothing at all. Most of the time, these random changes just jiggle the climate a little bit. A colder year here, a warmer year there. But every once in a while, the random noise lines up with the regular push from the orbit, and that's when something big can happen. The system flips, the ice sheets grow or they melt. The climate swings from cold to warm, or the other way around. This idea helps explain why the timing of ice ages is so regular, even though the changes in sunlight are so small. It's not just about the size of the push, it's about the timing and the way the system reacts to both regular and random forces. Let's get a bit more concrete. Scientists have run computer models where they try to build an ice age. They put in the small changes from Earth's orbit, then they add some noise, random changes in temperature, or in how much snow falls year to year. When they do this, something surprising happens. The climate in the model starts to jump from warm to cold and back on a regular schedule. Even though the pushes are small and the noise is random, together they create a steady rhythm. Every 100,000 years, the system flips. That's the heart of stochastic resonance. The climate system is sensitive, not just to the big things, but to the small random changes too. When you combine a weak regular force with a bit of chaos, you can get a much bigger effect than you'd expect. Here's another way to think about it. Imagine you're trying to roll a heavy ball over a small hill. If you push gently, nothing happens. The ball just rolls back. If you give it a huge shove, you might get it over the top. But what if the hill is a little bumpy, and every so often the ground shakes just enough to nudge the ball close to the edge? Most of the time, these shakes don't do anything. But if you time your push with one of those shakes, You only need a little force to get the ball over. The ball's movement isn't just about your push, it's about the push and the bumps working together. For Earth, the bumps are those random changes, volcanoes, ocean shifts, even sudden changes in sea ice or dust. The push is the slow, steady change in sunlight from the orbit. And when the two line up, the climate tips. This idea can be hard to picture, but it shows up in other places too. Sometimes small regular signals are hidden by noise, but if the noise is just right, it can actually help the signal stand out. That's what stochastic resonance is all about. A little bit of chaos can actually make a pattern stronger, not weaker. And here's the wild thing. Scientists have tested this idea in the lab, not with the whole planet, of course, but with simple systems. They use electrical circuits or even tanks of water. They add a small, regular signal, like a very gentle pulse, then they add some random noise. When they tune the noise just right, the system starts to jump in time with the pulse. It's like magic. Too little noise, and nothing happens. Too much noise, and it's just chaos. But with just the right amount, the pattern appears. So what does this mean for ice ages? It means that the planet's climate can act like one of these systems. The changes in Earth's orbit are the regular pulse. The random stuff, volcanoes, ocean shifts, dust storms, are the noise. When both come together at the right moment, the climate can flip from one state to another. This explains something else too. If you look at the history of ice ages, you'll notice they're not exactly the same every time. Sometimes the swings are bigger, sometimes a bit smaller. Sometimes the planet warms up a bit earlier, sometimes later. The timing is regular, but not perfect. This fits with the idea of stochastic resonance. The system is being pushed by a regular force, but it also depends on random events. Let's talk about numbers for a second. The changes in Earth's orbit, those Milankovitch cycles, change the sunlight by only about 1 or 2%. Not much. But the ice ages are huge events. Ice sheets thousands of feet thick, changes in sea level over 400 feet. That's a giant swing, all from a tiny push and a bit of noise. One of the clearest signs of this comes from the ice cores in Antarctica and Greenland. When scientists drill deep into the ice, they see layers going back hundreds of thousands of years. In those layers, they find signs of sudden jumps, abrupt changes in temperature, greenhouse gases, even dust. These jumps often line up with the timing of the orbital cycles, but they're not always exactly on schedule. Sometimes a random event seems to help tip the system. A big volcano or a sudden change in the ocean can be enough to push the planet over the edge. Another clue comes from the sea floor. In the mud under the ocean there are layers that show when ice sheets grew and shrank. These layers match up with the ice cores and with the timing of the orbit changes, but again, the record isn't perfect. There are small wobbles, and times when the system seems to skip a beat. That's what you'd expect if stochastic resonance is at work. The system is regular, but not a perfect metronome. And here's a twist. Before about 1 million years ago, Ice Age rhythm was different. The planet flipped from cold to warm about every 41,000 years, not 100,000. That matches a different kind of orbital change, the tilt of Earth's axis, which changes how sunlight hits the poles. But then, about 1 million years ago, the rhythm shifted to this longer 100,000-year beat. Scientists call this the mid-Pleistocene transition. Nobody knows exactly why the system changed gears, but it suggests that the way noise and regular pushes interact can change over time. Maybe the ice sheets got bigger and more stable. Maybe the ocean changed the way it stores heat and carbon. The rules of the game shifted. let's come back to what all this means. The story of ice ages isn't just about one thing. It's not just the orbit or just the ocean or just CO2. It's about how small, steady changes and random, unpredictable events can team up to make something much bigger than either one alone. Think of it like a lock and a key. The orbit is the key, turning slowly and steadily. The noise is like your hand shaking the lock a bit as you turn. Sometimes the key and the shake line up, and the lock opens. The system flips from one state to another. This idea doesn't just help explain ice ages, it's a reminder that nature is full of surprises. Sometimes a little bit of randomness is exactly what you need to bring out a hidden pattern. The world isn't always smooth and predictable. Sometimes chaos helps make order. There's something comforting about this, in a strange way. The Earth isn't just a giant clock ticking off the years, it's a living, breathing system. It responds to small nudges and big shocks. Sometimes it does the unexpected. But even in the middle of all that chaos, there's a rhythm, a pattern you can see if you look from far enough away. So, when you hear that ice ages come and go every 100,000 years, remember this. It's not just the math of orbits. It's not just the slow build-up of ice, or the sudden release of carbon. It's the dance between order and chaos, the push and the random noise. Together they make the climate swing. And this idea, stochastic resonance, is one of the best theories we have for why the timing of ice ages is so regular. It's not a perfect answer. There are still mysteries. We don't know exactly what all the sources of noise are. We're still learning how the ocean, the atmosphere, and the ice all work together. But it's a good start. It shows that even the biggest swings in Earth's history can come from small beginnings. A tiny push here, a random nudge there, and the whole world can change. Sometimes that's all it takes. And here's the big picture. Earth's climate system is balanced on a knife edge. It only takes a little push and maybe a bit of luck to tip it from one state to another. The regular beats of the orbit give us the rhythm. The noise gives us the surprise. So, next time you wonder why the planet freezes every 100,000 years, think about swings, locks, and noisy systems. It's not just the strength of the push. It's when the push and the noise come together. That's when the magic happens. But there's still more to the puzzle. All of this, the orbits, the noise, the ice, the ocean, works together in ways we're only beginning to understand. And if you look back far enough, you'll see something even stranger. About 1 million years ago, everything changed. The rhythm of ice ages slowed down. Something in the system shifted. And scientists are still trying to figure out what happened and why. Let's take a look at that next. Let's really dig into this mystery. About 1 million years ago, the rhythm of ice ages on Earth changed. Before that, the planet slipped in and out of deep freezes every 41,000 years. Then, all of a sudden, the pace slowed down. Now it was every 100,000 years. That's a huge jump. It's like a clock suddenly ticking at half speed for no obvious reason. This big shift has a name, the Mid-Pleistocene Transition. Scientists call it the MPT for short. It happened somewhere between 1.2 million and 700,000 years ago. The exact date is still fuzzy, but the evidence is clear that it happened. We know about this change because of clues buried deep in the earth. If you look at mud from the bottom of the ocean, you'll see layers stacked on layers, like pages in a really old book. Each layer tells a story about what the world was like when that mud settled. By studying tiny shells and chemicals in these layers, scientists can figure out how much ice was on land, how warm or cold the ocean was, and even what the air was like. What they found is pretty wild. For more than 1,000,000 years, the main pattern was a 41,000-year cycle. Ice sheets grew and shrank following changes in how much Earth tilts on its axis. The tilt changes slowly, which shifts how much sunlight hits the poles. That's what set the pace. But then, something happened. The cycles got longer. The ice ages started coming every 100,000 years instead. The swings between warm and cold became bigger. Ice sheets grew taller and stretched farther south. The changes in climate became more dramatic. Why did this happen? That's the big question. The tilt of the Earth didn't slow down. The orbit didn't change its basic rhythm. Something else must have shifted. But what? Let's start by looking at the evidence itself. The mud, the ice, the dust, and the fossils. Each one gives us a different viewpoint, like looking at an old crime scene from several angles. First, the seafloor mud. When scientists drill into the ocean floor, they pull up long tubes of sediment. Each inch can hold thousands of years of history. In these tubes they find tiny fossils called foraminifera. People just call them forams. These are tiny sea creatures with shells. When they were alive, their shells soaked up oxygen from the water. Some kinds of oxygen are heavier than others. The ratio between the heavy and light types changes with temperature and with how much water is locked up in ice sheets. So by measuring these ratios in the shells, scientists can make a timeline of when ice sheets grew and melted. It's like reading an ancient thermometer that never broke. When they plot these ratios over time, a clear pattern jumps out. Before 1,000,000 years ago, the biggest swings line up with the 41,000-year tilt cycle. After that, the swings get bigger and the timing shifts to every 100,000 years. The evidence is strong. It's not just one spot in the ocean either. They see this pattern in mud from every ocean basin. Atlantic, Pacific, Indian, Southern. The whole planet changed gears. Next comes the evidence from ice cores. These are long cylinders of ice drilled from deep in places like Antarctica and Greenland. Each layer in the ice is a little bit of ancient snow pressed down over thousands of years, air bubbles trapped in the ice-hold samples of old atmospheres. By counting layers and measuring chemicals, scientists can see how temperature, carbon dioxide and dust levels changed over time. The ice cores only go back about 800,000 years, so they don't cover all of the MPT. But they do show the 100,000-year pattern very clearly. During cold times, called glacials, the ice is thicker and dustier. Air bubbles show lower levels of carbon dioxide. In warmer times, called interglacials, the ice thins, dust drops, and carbon dioxide rises. These cycles line up with what the ocean mud shows. But here's something interesting. Right around the MPT, the swings in carbon dioxide get bigger. Before the transition, the changes are smaller and smoother. After, the highs get higher and the lows get lower. The climate system starts acting more extreme. Now let's talk about rocks on land. In some places you'll find layers of dirt, gravel, and even big boulders called moraines. These were left behind by glaciers as they grew and shrank. By dating these rocks with special techniques like counting rare atoms made by cosmic rays, scientists can tell when glaciers moved and how far they reached. The story these rocks tell matches the mud and the ice. Before the MPT, glaciers were smaller. They advanced and retreated more often. After the transition, glaciers grew much larger, but moved less often. When they did move, it was a big deal. Huge walls of ice grinding across the land, carving valleys, shifting rivers. Fossils add another clue. In caves and old riverbeds, bones and plant remains show what kinds of animals and plants lived during different times. Around the MPT there's a shift. Some species disappear, others move to new places. Plants that like cold weather spread farther south. Animals that need warmth retreat or vanish. The landscape itself seems to change as the climate becomes more unpredictable. Even ancient dust helps tell the story. During the coldest parts of these cycles, strong winds picked up huge clouds of dust and dropped them all over the planet. In China, for example, thick layers of dust called loess stack up like a layer cake. Each layer matches a cold, dry period when ice sheets were biggest. The pattern of thick and thin layers changes after the MPT, matching the new, longer cycles. So the evidence from all these sources, ocean mud, ice, rocks, dust and fossils, lines up. The pace of climate change on Earth shifted about 1 million years ago. The swings got bigger, the cycles grew longer, and life on the planet had to adapt. But what could cause such a big change? The tilt of the Earth kept its rhythm. The orbit still cycled. The sun didn't suddenly get brighter or dimmer. So what happened? One idea is that the ice sheets themselves learned to behave differently. Picture the ice as a giant, slow-moving animal. Before the MPT, the ice sheets were smaller and more fragile. They grew and melted, easily following the 41,000-year tilt cycle. But over time, maybe the ice sheets got thicker and tougher. As they grew, they pressed down on the crust, making big dents in the land. This changed the way water flowed, and even how the land bounced back when the ice melted. As a result, the ice sheets could survive through the smaller changes in sunlight. They only melted when there was a really big push, like when the orbit and the tilt lined up just right, or when something else, like a sudden burst of warmth, gave them a shove. This made the cycles longer and the swings bigger. There's some evidence for this. In the ocean mud, scientists see signs that ice sheets after the MPT were thicker and lasted longer. The rock records show bigger moraines left behind, and computer models suggest that once ice sheets reach a certain size, they become much harder to melt. Another idea is that something changed in the way the ocean moves heat and carbon around. The deep ocean is like a giant storage tank for cold water and carbon dioxide. If the way water flows in the deep ocean changed, it could make the climate system more sensitive. It might have trapped more carbon dioxide for longer periods, making cold times even colder. Then, when the system finally flipped, it would release a lot of carbon dioxide at once, making warm times even warmer. There's some support for this in the chemical clues from ocean mud. After the MPT, the deep ocean stored more carbon during ice ages, and when the ice melted, huge amounts of carbon were released quickly. There's also the idea that slow changes in the shape of Earth's continents played a role. Over millions of years, land shifts very slowly. Maybe mountain ranges grew higher, or land bridges appeared and disappeared. These changes could have shifted wind patterns, changed how much snow fell, or affected ocean currents. All of these could make ice sheets grow bigger and last longer. Here's another twist. Scientists wonder if tiny changes in the way Earth spins, called precession, might have stacked up over time. Maybe as these smaller cycles added up, they pushed the system into a new pattern. It's like a bunch of small clocks ticking together, and every so often their alarms all go off at once. But none of these ideas has a perfect answer. Each one explains part of the story, but not the whole thing. The change at the MPT is still a real puzzle. Let's look at some numbers to make this more real. Before the MPT, the ice ages lasted about 41,000 years. The ice sheets advanced, then melted, then advanced again. Each time, sea levels dropped by about 200 feet, then rose again. After the MPT, the swings got bigger. Ice ages lasted around 90,000 years, with only brief warm periods in between. Sea levels dropped by as much as 400 feet, then shot back up in just a few thousand years. That's a huge change for life on Earth. If you lined up all the Ice Age cycles from the last 2.5 million years, you'd see this pattern shift clearly. It's like a heartbeat that suddenly slows, then starts pounding harder. What about life during this time? The mid-Pleistocene transition wasn't just a climate story. It was a time of change for the plants, animals, and even the early humans living on Earth. As ice sheets grew larger, forests shrank and grasslands spread. Animals like mammoths, giant deer, and woolly rhinos did well in the cold. Others struggled or disappeared. Some scientists think these changes helped drive evolution. New species appeared, old ones vanished, and the survivors adapted to a world that changed more slowly but more dramatically with each swing. Now, let's talk about how we know all this is real, and not just a trick of the data. Scientists have checked these patterns using different clues from all over the world. Ocean mud, ice cores, rock layers, cave formations, and even ancient pollen. They all show the same shift. It's not just one spot or one kind of evidence. The whole planet changed together. There are even ways to check the timing. For example, in Italy there are caves where limestone grows in thin sheets, layer by layer. These speleothems, people just call them cave formations, grow faster in warm, wet times and slower in cold, dry times. By measuring the layers and using radioactive dating, scientists can match cave records to the ocean mud and ice cores. The times line up almost perfectly. The shift to longer cycles shows up everywhere you look. It's like piecing together a giant jigsaw puzzle. Each clue on its own is interesting, but when you put them all together, you see the big picture. The planet's climate had a major shift about 1 million years ago. The new rhythm has lasted ever since. But the why is still mysterious. Maybe it's a little bit of everything. The ice sheets got bigger and heavier. The ocean stored more carbon. The land changed shape. The cycles of tilt, orbit, and spin all lined up in a new way. And then, one day, the system flipped. Since then, Earth's ice ages have marched to the long, slow 100,000-year beat. Some scientists think that the system reached a tipping point. Once the ice sheets got big enough, and the ocean's carbon cycle changed enough, there was no going back. The climate settled into a new pattern. Now it takes a much bigger push to melt the ice sheets. The planet spends more time in cold states, with only brief windows of warmth. There's also an idea that feedback loops became stronger. Feedback is when a small change causes bigger changes that make the first one stronger. For example, when ice grows, it reflects more sunlight, making things even colder. When ice melts, the ground soaks up more sun, making things warmer. After the MPT, these feedbacks might have gotten stronger. That would make the swings between ice and warmth more dramatic. And here's something to think about. The MPT shows how a small change, like thicker ice sheets or a shift in ocean currents, can set off a much bigger change in the whole system. The climate isn't just a simple machine. It's full of tipping points, feedbacks, and surprises. Even after decades of research, the mid-Pleistocene transition is still one of the biggest puzzles in climate science. The evidence is clear that something changed. The exact reason is still up for debate, but the story is far from over. New discoveries keep coming. Every year, scientists drill new cores, find new fossils, and invent better ways to measure old clues. Each new piece brings us a little closer to understanding what happened. And here's a fun twist. Our own story, humans, starts to pick up right around this time. Early humans were already on the scene before the MPT. But as the climate shifted, so did they. The changing world may have helped shape our brains, our bodies, and our ability to survive in a world that never stays the same for long. So next time you hear about the ice ages, remember the strange twist 1,000,000 years ago. The planet's heartbeat slowed. The swings got bigger. Nobody knows exactly why. But the signs are everywhere. In ocean mud, in ice, in rocks, in the bones of lost animals. The Earth remembers. And that's why scientists are still digging, drilling and exploring. They're looking for the missing piece of the puzzle. Because the story of the mid-Pleistocene transition isn't just about the past. It has something to tell us about how small changes can lead to big shifts, even today. So what does all this mean for our future? Let's zoom in on the time we're living in right now. The current interglacial. This is the warm stretch between ice ages. Scientists call it the Holocene. It started about 11,700 years ago. That might sound like a long time, but on the scale of Earth's history, it's just a blink. Think about this. If the whole history of the planet was a year, the Holocene would be a few seconds before midnight on December 31st. So what's special about the Holocene? Well, for one thing, it's when people built everything you know. Cities, farms, writing, all of it. Before this time, life was wild and cold. Now the land is mostly green, the ice sheets are small, and the climate has been, at least until recently, pretty steady. But how do we know how unusual the Holocene really is? And what makes this warm period different from all the other warm spells in the past? Let's dig into the evidence layer by layer and see what the planet has to say. First, let's start with the ice. Even though glaciers melted back at the end of the last ice age, a few giant ice sheets are still left, mostly in Greenland and Antarctica. But during the last glacial maximum, which was only about 20,000 years ago, things looked totally different. Huge sheets of ice covered Canada, northern Europe and parts of Asia. If you lived back then, you would have seen walls of ice taller than skyscrapers, stretching for thousands of miles. As the world slowly warmed, the ice sheets shrank. Ocean levels started rising, swallowing up land bridges that once connected continents. That's why you can't walk from Siberia to Alaska now, but people could during the Ice Age. The evidence for this is everywhere. You can find old shorelines far inland where the sea used to reach. In some places like Scandinavia, the land is still slowly rising, bouncing back from the weight of the old ice. Now, let's look at the mud at the bottom of the sea. Remember those tiny fossils, the forams? When you look at the layers from the Holocene, you see a huge change. The shells show that the ocean warmed up fast. The amount of carbon dioxide in the air jumped, and the chemistry of the water changed. These shifts all line up with the melting of the ice and the start of the new warmer age. But here's something cool. The Holocene isn't the only warm spell in the last 1,000,000 years. There have been at least 8 or 9 other interglacials since that big shift to 100,000-year cycles. Some were longer, some shorter, some were warmer, some cooler. But they all shared one thing. They were brief islands of warmth in a long sea of cold. Scientists figure this out by looking at ice cores from Antarctica and Greenland. Each layer of ice is a slice of old climate. By measuring bubbles of ancient air and looking at dust and chemistry, they can build a record that stretches back almost 1,000,000 years. The pattern is clear. Every 100,000 years or so, the world warms up for a short time, usually about 10,000 to 15,000 years. Then, almost like clockwork, the ice returns. Let's talk numbers for a minute. During the coldest parts of the last ice age, average global temperatures were about 9 degrees Fahrenheit colder than today. That might not sound huge, but it's the difference between an ice-covered Canada and the forests we see now. Sea levels were about 400 feet lower. You could walk from what's now England to France. Mammoths and woolly rhinos roamed the plains. Then, about 20,000 years ago, the world started to warm. By 14,000 years ago, the ice sheets were melting fast. Huge floods poured into the oceans. Sometimes lakes trapped by ice would burst, releasing more water all at once. The landscape changed quickly. Forests and grasslands spread north as the ice retreated. Animals followed. So did people. The start of the Holocene wasn't smooth. There were wild swings like the Younger Dryas, a sharp cold snap that lasted about 100–200 years. Evidence for this comes from pollen in ancient lake mud and from tiny crystals in Greenland ice. Suddenly, right near the end of the Ice Age, temperatures dropped back down. Then just as fast, the cold ended and the world warmed again. Once the Holocene really began, things settled down. For the last 11,700 years, the climate has been unusually stable. Temperatures have gone up and down a little, but not by much. The pattern is almost flat compared to the wild swings before. Scientists even call this time the long summer. Why is this important? Because stability gave humans a chance to build. Before the Holocene, humans lived by hunting and gathering. They moved when the weather changed, following animals and wild plants. But once the climate steadied, people could start farming. They planted crops, raised animals, and stayed in one place. Villages grew into towns. Towns grew into cities. Civilizations rose all over the world. So how do we know the Holocene was really stable? And not just in one place, but everywhere? The answer comes from dozens of clues. There are tree rings, which show how wet or dry each year was. There's pollen in lake mud, which tells us what kinds of plants were growing. There are cave formations like stalagmites and stalactites, which grow faster or slower depending on rainfall and temperature. All these records line up. The Holocene has been a time of calm, but it hasn't been completely flat. There were smaller wiggles in the climate. For example, about 800–200 years ago, there was a sudden cold snap that lasted for a century or two. Scientists think it was caused by a giant lake in North America draining into the Atlantic, changing ocean currents. There was also the so-called 4.2 kiloyear event about 400–300 years ago. That was a drier, cooler period that hit ancient Egypt and Mesopotamia hard. Some kingdoms collapsed, others barely survived. Then there was the medieval warm period, about 1,000 years ago, when parts of Europe got warmer. Vikings sailed to Greenland and even North America. Later came the Little Ice Age, from around 1300 to 1850. Winters in Europe were colder, rivers froze, and crops sometimes failed. But even these changes were small compared to the giant swings of the Ice Age. Let's pause for a second and think about what the evidence actually shows. In Greenland ice cores, the layers from the Holocene are thicker and more even. There are fewer big dust spikes. The amount of carbon dioxide in the air stays steady, within a narrow range, about 260 to 280 parts per million until very recently. Tree rings from all over the world show the same thing. Some years are better than others, but the pattern is gentle. No deep freezes, no wild heat spikes. This climate calm is a rare thing in Earth's story. If you look back over the last million years, most of the time was cold, dry, and hard. Warm periods like the Holocene are short and precious. They're like breathing spaces between long, icy winters. Now let's talk about the animals and plants. During the Holocene, forests grew back where ice had scraped the land bare. Animals like deer, wolves, and bison spread into new areas. Some big creatures from the Ice Age, like mammoths and giant sloths, didn't make it. They vanished as the climate warmed and people spread out. But many species found new homes. There's also a story in the mud at the bottom of lakes and oceans. Layers from the Holocene are full of pollen from trees and grasses. You can see forests marching north over thousands of years. In some places, ancient seeds and leaves are still preserved. They show how fast the world changed as the ice retreated. In Europe, the forest came back first in the south, then spread north as it warmed. In North America, the same thing happened. Birch and pine gave way to oak and maple. Animals followed the trees. People did too. The story repeats in Asia, Africa, and South America. The evidence is everywhere, in cave paintings, in ancient campsites, in piles of shells left by people eating by the sea. Life changed with the land. But the Holocene isn't just a story of nature, it's the stage for human history. The first farms appeared in the Middle East about 10,000 years ago. Wheat, barley, and lentils were planted. Sheep and goats were tamed. Soon rice farming began in China. Corn, beans, and squash were raised in the Americas. All this happened during the Holocene. Without a stable climate, it probably wouldn't have been possible. Let's look at some numbers again. The world's population before farming was small, maybe a few million people, scattered in tiny bands. By the time the first cities rose around 5,000 years ago, there were tens of millions. Today, there are over 8 billion. That's a huge change, and it all happened in this warm window. What about the world's ice? Greenland still holds a big ice sheet, but it's much smaller than during the Ice Age. Antarctica is even bigger, but it's far from most people. The last bits of ice in North America and Europe melted away about 8,000 to 6,000 years ago. The evidence shows this clearly. Old shorelines, buried soils, and ancient pollen tell the story. Sea levels rose fast as the ice melted. In some places, the ocean swallowed up land that people once lived on. There are even underwater ruins off the coasts of India and the Mediterranean. People had to move as the seas came in. Let's not forget about climate surprises. Even in the Holocene, there were droughts and floods. Droughts hit North Africa about 5,000 years ago, turning green grasslands into the Sahara Desert. Evidence for this comes from ancient lake beds, buried sand dunes, and even cave art showing animals that don't live there now. Other places got wetter for a while. The monsoon shifted in Asia, flooding some regions and drying out others. These changes show up in river mud, lake layers, and even in the rise and fall of ancient kingdoms. But again, none of these shifts match the wild swings of the Ice Age. Now, what about carbon dioxide and greenhouse gases? For most of the Holocene, carbon dioxide stayed in a narrow band like we said before. That's what you see in ice cores. Only in the last 2 centuries has it shot up, mostly because of burning coal, oil and gas. This is a new thing, and scientists are watching closely to see what happens next. But let's stay with the past for a moment. The calm of the Holocene wasn't guaranteed. It was just good luck in a way. The planet's orbit, tilt and wobbles lined up to give us a break between ice ages. If you look at the timing, we're right about due for another cold period, at least by the old pattern. But something is different now. The amount of greenhouse gases in the air is higher than at any time in the last 800,000 years. The world is warming fast. This isn't what usually happens near the end of an interglacial. Scientists are still trying to figure out exactly what this will mean. For most of the Holocene, life was shaped by gentle changes. Rivers shifted, forests grew and shrank. People learned to farm and animals found new places to live. The evidence for all this comes from rocks, mud, ice, pollen, tree rings, and even from human bones and old tools, you can see the traces of ancient farming in the soil. There are old fields in England, rice paddies in China, terraces in Peru. All these are marks of people using the calm weather to build something lasting. So what's the takeaway from all this? The Holocene is rare. It's a gift from the planet's strange heartbeat, a pause between long, freezing winters. It's been steady, but not perfectly calm. There have been bumps and chills, but compared to the wild rides before, it's been paradise. All the evidence lined up. Ice cores, mud, pollen, tree rings, lake layers, ancient shorelines. They all tell the same story. A long, warm window, just right for humans to settle down and build. Will it last? That's the big question. If the pattern of the last million years holds, another ice age should be coming, someday. But with the new spike in greenhouse gases, the future is wide open. The story of the Holocene is really the story of us. We're here because the world got lucky. The evidence is everywhere, if you know where to look. In the quiet layers of mud, in frozen air bubbles, in the rings of old trees, in the seeds of ancient farms. It's strange to realize how much depends on a planet's rhythm. One long summer, and here we are. Cities, science, art, all of it. The calm between the storms. So when you look at a map or watch the seasons change, remember this isn't normal for Earth. It's special, and it won't last forever. What can we learn from this 100,000-year heartbeat? That's the next mystery. Let's step back and look at the really big picture for a minute. Not just a few thousand years or even a few ice ages. Let's talk about deep time, the kind of span that makes your head spin. This is the world as it looks when you zoom out, way out, far beyond human history, beyond even the first people. We're talking about hundreds of thousands, even millions of years. It's hard to imagine, but understanding deep time is the only way to see why the planet keeps freezing and thawing over and over. So what does deep time look like? Imagine a timeline stretched across your whole neighborhood. The part with people, cities and farms would be a tiny scratch at one end. Most of that timeline would be empty of us. It's full of things we can barely picture. Strange animals, shifting continents, and endless cycles of ice and fire. Here's the thing about Earth. It's always changing, but not in a smooth, gentle way. It swings between extremes. For most of its history, the planet has been either much hotter or much colder than it is now. The last few million years, though, have been special. That's when the cycle of ice ages really kicked in. Sometimes the world is covered in ice. Sometimes it's warm and green. But those flips don't happen randomly. They follow a pattern. Scientists call this the Ice Age cycle. It's not just one long ice age. Instead, ice comes and goes in waves. Cold stretches last for about 90,000 years. Then there's a short warm break, an interglacial like the Holocene, which we're living in now. Then the ice returns. It's like a breath in and out, but each breath takes 100,000 years. But why? What sets the rhythm? To answer that, we have to talk about things even bigger than the Earth itself. We have to look at the sky. Here's where it gets really interesting. The main driver behind these giant swings isn't volcanoes or meteor strikes. It's the way the planet moves through space. Earth doesn't just spin and go around the sun in a perfect circle. Its path is a little bit messy. The orbit wobbles. The tilt of the axis shifts. The shape of the path around the sun changes. These slow, steady changes are called Milankovitch cycles, after a Serbian scientist named Milankovitch who figured them out about 100 years ago. Let's break it down. There are three main things going on. First, there's the shape of Earth's orbit. Sometimes it's more like a circle. Sometimes it's more like an oval. This cycle takes about 100,000 years. When the orbit is more oval, Earth gets closer and farther from the Sun during the year. That changes how much sunlight reaches different parts of the planet. Second, there's the tilt of Earth's axis. Right now, the planet is tilted about 23.5 degrees, but this angle changes over time, swinging between about 22 and 24.5 degrees. This tilt cycle takes about 41,000 years. When the tilt is bigger, summers are hotter and winters are colder, especially near the poles. When the tilt is smaller, you get milder seasons. Third, there's a wobble called precession. Imagine a spinning top slowly tracing a circle as it leans over. Earth does the same thing, but much more slowly. This wobble takes about 26,000 years to complete a loop. It changes the timing of the seasons, making northern summers happen at different points in the orbit. Now, these three cycles don't line up perfectly. Sometimes they add up to make summers in the north really strong. Sometimes they cancel each other out, making for weak, cool summers. And here's the key. It's those northern summers that matter most for ice ages. Why the north? Most of the big land masses are in the northern half of the planet. That's where the giant ice sheets form during cold times. If summers there are weak, the snow from winter doesn't melt. Year after year, the ice builds up. If summers are strong, the ice melts back. So to sum up, every 100,000 years or so, the planet's orbit, tilt and wobble line up just right. Or just wrong, depending on how you like your weather. Summers in the north get weaker. Ice starts to build. Over thousands of years, glaciers grow and spread. Sea levels drop as water gets locked up in the ice. Then when the cycles shift again and summers get stronger, the ice melts away. Oceans rise. The world warms up. Plants and animals move north. People follow. But here's something weird. The timing of these cycles fits the evidence almost too well. When scientists drill into ancient ice or look at layers in the ocean floor, they see the same pattern again and again. Cold for about 90,000 years. Warm for about 10,000, then cold returns. The match with Milankovitch cycles is close, but not perfect. Some ice ages started a little early or late. Sometimes the planet stayed cold even when the cycles said it should warm up. This has led to a big puzzle. If the cycles are always running, why don't ice ages start and end at the exact same time? Every time? And what about greenhouse gases like carbon dioxide and methane? These also change during the ice age cycles. When the world warms, carbon dioxide goes up. When it cools, carbon dioxide drops. But which comes first? The warming or the rise in carbon dioxide? It's a classic chicken and egg problem. Here's what most scientists think happens. The cycles in Earth's orbit and tilt set the stage. They nudge the climate in one direction or another, but the planet's climate is like a giant complicated machine. If you push it a little, it can swing a lot. When the cycles make northern summers weaker, ice builds up. When the ice grows, it reflects more sunlight. This makes it even colder. More ice forms. It's a feedback loop. At the same time, the oceans and plants start to pull carbon dioxide out of the air as things cool down. Lower carbon dioxide makes the planet even colder. So a small push from the cycles turns into a big shift in temperature. When the cycles flip and summers get strong, the ice melts, carbon dioxide goes back up, and the planet warms fast. This is why the change from cold to warm and back again can be so sudden. Sometimes in just a few thousand years the whole world flips from icy to green. It's like a giant switch. But here's the twist. For most of the last 2 million years, the Ice Age cycle followed a 41,000-year rhythm. Then, about 1 million years ago, it slowed. Down, the cycle stretched out to 100,000 years. Nobody is exactly sure why. The best guess is that the ice sheets finally got big enough to change the rules. Once the glaciers reached a certain size, it took a bigger push to melt them, so the planet started following the longer cycle. This shift is still a mystery. Scientists call it the mid-Pleistocene transition. Before this, ice ages came and went more quickly. Afterward, the cold spells lasted much longer. The warm breaks, like the Holocene, became shorter and rarer. Think about this. For the last million years, most of the time the world has been frozen. Warm periods like ours are the exception, not the rule. If you randomly jumped back in time, you'd probably land in a cold, dry world, not a green one. Let's look at some numbers. Over the past 800,000 years, there have been about 8 or 9 full Ice Age cycles. Each one starts with a slow slide into cold. Ice sheets build up, sea levels fall, deserts spread. Then, a sharp jump up into warmth. The pattern is clear in the data from ice cores and ocean mud, but there are small differences in each cycle. Some warm spells last longer, some ice ages are colder. Why do these cycles matter for life on Earth? Because they shape everything: where animals live, what plants can grow, where the sea covers the land, even how people move and build. During the last ice age, giant mammals like mammoths, mastodons, and saber-toothed cats roamed the cold plains. When the ice melted, forests returned and those big animals faded away. New species took their place. The Ice Age cycles also created land bridges like the one between Asia and North America. When sea levels dropped, people and animals could walk from one continent to another. When the ice melted, the bridges disappeared and the world map changed again. But deep time isn't just about the ice ages. If you zoom out further, you see even bigger swings. There were times when the whole planet was covered in ice. What some scientists call snowball Earth. Other times, like during the age of dinosaurs, the world was much warmer than today. No ice at the poles. Thick forests grew near the Arctic Circle. Sea levels were hundreds of feet higher. The Ice Age cycles are just the latest chapter in a long, wild story. They started a few million years ago, probably because of slow changes in the way continents were arranged. As the land moved around, ocean currents shifted. Mountains rose, changing the wind and rain. Antarctica drifted over the South Pole and froze over. All these changes made the planet more sensitive to the cycles from space. So when you hear people talk about normal climate, remember, there is no normal. The planet is always in motion. Deep time shows us that change is the only constant. Sometimes the change is slow, sometimes it's fast, but it never stops. Think about the evidence. It's all over the world. In Greenland and Antarctica, ice cores show the swings from cold to warm. In deep-sea mud, the shells of tiny creatures record changes in temperature and chemistry. In ancient lake beds, you can see layers that mark wet times and dry times, cold snaps and warm spells. Even in the rocks under your feet, there are clues. Fossils of plants and animals that lived in totally different climates. Here's a simple example. In Europe, scientists have found pollen from trees that only grow in warm, wet climates, right in the middle of layers from an ice age. That means the climate flipped back and forth, sometimes quickly. In North America, giant boulders called glacial erratics sit far from any mountains. They were carried there by ice sheets, dropped when the ice melted. The ocean floor tells another story. Layers of mud build up one on top of the other. Each one holds tiny fossils that show what the temperature and chemistry were like. Scientists can use these to make a record going back millions of years. The pattern matches what we see in the ice. cold, then warm, then cold again. There's another clue in the ancient coral reefs. Some reefs are now high and dry, far above sea level. That means the sea was higher in the past. Other reefs are drowned, deep under the ocean. That means sea level was lower when they grew. All these pieces fit together to show the same cycles. Now let's talk about feedbacks. These are the ways the climate system can speed up or slow down changes. Ice is a big one. When more land is covered in snow and ice, more sunlight gets bounced back into space. That makes the planet colder, so even more ice forms. The opposite happens when ice melts. Darker land and water soak up more heat, making things warmer. Greenhouse gases are another feedback. When the world is cold, the oceans soak up more carbon dioxide. When it warms up, the oceans release that gas back into the air. Plants grow faster in warm times, pulling carbon dioxide out. Big changes in forests and grasslands can shift this balance. These feedbacks help explain why the swings between ice ages and warm periods are so sharp. But not all feedbacks are positive. Sometimes things can slow changes down. For example, as ice sheets grow, they get so heavy they press the land down. This can change the way rivers flow and where rain falls. These shifts can make it harder for ice to keep growing in some places, and then there's randomness, things that don't follow any pattern. Big volcano eruptions can cool the planet for a few years. An asteroid impact can shake things up for decades. But these are rare. Most of the time, the slow, steady push of the cycles is what matters. Some people wonder if life itself can change the climate, and it can. Plants, especially forests and plankton in the ocean, help control the amount of carbon dioxide in the air. When big forests grow, they pull carbon out. When forests die or burn, that carbon goes back into the sky. Over millions of years, this helps set the planet's thermostat. So what does all this mean for us? It means the present moment is a lucky break. For most of deep time, things weren't so easy. Earth was either much too cold or much too hot for people to thrive. Our whole stretch of history, from cave paintings to space travel, fits inside just one warm blip in a long, icy story. And here's another thing. The cycles don't care about us. They'll keep rolling, whether humans are here or not. We just happen to be living in a rare window when the world is friendly. The weather is mild and life can spread out and build. If you ever feel small, remember, every breath you take, every city, every poem is balanced on the tip of these giant cycles. We're riding the wave of deep time. The ice will come again someday. Or maybe, now that humans are changing the atmosphere, the pattern will break. Either way, deep time reminds us that nothing stays the same. What feels normal is really just a pause in a much bigger story. And now, as you drift towards sleep, so what can we really take away from all of this? Why does it matter that Earth freezes and thaws every 100,000 years? Why spend all this time talking about ice, cycles, and deep time? Let's start with something simple. These cycles aren't just background noise. They've shaped every part of the world we know. If you look at a map, the mountains, rivers, and lakes, so many of them are leftovers from the last ice age. The big flat plains in North America and Europe, smoothed out by glaciers, the Great Lakes, carved by ice and then filled with meltwater. Even the soil in your backyard, if you live in the north, was scraped up and left behind by a moving wall of ice. It goes further. The places where people live today, the routes we take, even the foods we grow, they all trace back to these ancient rhythms. Crops like wheat and barley got their start after the last ice melted. The forests and grasslands you see are the result of thousands of years of slow warming. Even the animals that survived, from deer to rabbits to songbirds, are the ones that could handle these wild swings. But here's where it gets interesting. If you zoom out, you start to see how fragile this moment is. Human civilization, cities, writing, farming, the whole thing, is a brand new experiment. Modern people have only been around for about 300,000 years. But for most of that time, life was tough. The world was cold, dry, and dangerous. People moved with the seasons, following herds and searching for places to survive. Sometimes, whole groups disappeared when the ice pushed too far. We got lucky. The last 10,000 years have been unusually warm and stable. That's when people learned to farm. They built villages, then towns, then cities. Rivers stayed in their banks. The weather was predictable enough for crops to grow. This short window, just a blip on the timeline, gave us a chance to build everything we know, but the ice is never far away. There are clues everywhere. In Europe you can find rocks called erratics that were carried hundreds of miles by glaciers. In Africa, old riverbeds show where water once flowed during wetter times. In South America, fossils of giant sloths are found in places that are now dry grassland. All these signs point to a world that's always shifting. Let's talk about people for a minute. Imagine being alive 20,000 years ago, near the end of the last ice age. The world would feel harsh and empty. Huge ice sheets would block the north. Mammoths and woolly rhinos would roam the cold plains. People would live in small groups huddled around fires, always on the move. Food would be scarce. Winters could last for years. But these people were tough. They made tools from stone and bone. They learned to sew warm clothes from animal skins. They painted pictures deep inside caves, maybe as a way to make sense of the world, or just to leave a mark. When the ice finally melted, some groups moved north following animals and fresh land. Others stayed in the south, learning new ways to live as the climate changed. Now look at us. Most people don't worry about the next ice age. We have houses, heaters, and supermarkets. But the cycles are still running in the background. The same changes in Earth's orbit and tilt are still happening, slow as ever. If nothing else changed, another ice age would start in tens of thousands of years. But things are different now. Over the last 200 years, humans have started to change the atmosphere. We burn coal, oil, and gas. We cut down forests and build cities. All this adds carbon dioxide to the air, a gas that helps trap heat from the sun. This is new. It's something the planet hasn't seen before, at least not this fast. Scientists are now asking a big question. Will the next ice age ever come? Or have we changed the rules? Some studies show that the extra carbon dioxide we've added could push the next ice age far into the future. Maybe tens of thousands, maybe even hundreds of thousands of years. Nobody can say for sure. Think about that for a second. For millions of years the world has flipped between cold and warm. But now, because of us, that pattern might be broken. We've become part of the story, not just as passengers but as drivers. This brings up another point. Earth's climate isn't just about numbers and cycles, it's about life. Every time the world shifts, animals and plants have to move, adapt, or die out. When the ice comes, forests shrink and grasslands spread. When it melts, trees grow back and new animals appear. These changes can be slow or fast, but they always leave a mark. Sometimes whole groups vanish. The big animals from the Ice Age, mammoths, saber-toothed cats, giant ground sloths, are all gone now. Some disappeared when the world warmed up. Others may have run into trouble when people arrived, hunting them or taking over their land. Every cycle leaves winners and losers. People are good at adapting. We learned to fish, farm and build. We crossed land bridges and sailed the seas. But even for us, big changes are hard. When climates shift quickly, there's less time to adjust. Crops might fail, rivers could dry up or flood. New diseases can spread as animals and insects move to new places. It's a reminder that we don't control everything. The planet is huge and complicated. Even small pushes like a shift in sunlight or a change in carbon dioxide can tip the balance. Sometimes all it takes is a little nudge to set off a big chain reaction. Here's something humbling. Fossils show that life has survived much worse. There were times when almost everything died out, like the mass extinctions that wiped out the dinosaurs, or the snowball Earth events when ice may have covered nearly the whole planet. Somehow, life bounced back. New forms appeared. The world kept spinning. But every time the survivors had to start over. The rules changed. What worked before didn't always work again. It's a pattern that repeats, but never in exactly the same way. So where does that leave us? We live in a world shaped by chance, cycles, and choices. We're here because of a long chain of events. Some we understand, some still a mystery. The ground beneath our feet, the air we breathe, even the weather outside, all shaped by forces we can't see. Some people find this scary, others find it comforting. There's a kind of peace in knowing that change is normal, that nothing lasts forever. The world is always moving. The ice will come and go. Warm times will return. Life will find a way, even if it looks different each time. Here's another way to think about it. History isn't just about people, kings, or wars. It's also about the land, the sky, and the deep rhythms of nature. If you go far enough back, you see that people are just one part of a much bigger story. The story of a planet that spins, tilts, and dances through space, always changing, always surprising. This doesn't mean we're powerless. We still make choices every day. The way we live, the things we build, the care we show for the land and water, all of it matters. We can't stop the cycles, but we can learn from them. We can try to be ready when things shift. We can pay attention to the clues the past has left for us. Think about how far we've come, from small bands of people hunting in the cold to cities that glow at night, from simple tools to rockets that leave the planet. All of this happened in a blink compared to deep time. It's easy to forget how new it all is. Sometimes it helps to slow down and listen, to see the world not just as it is, but as part of a long unfolding story. The wind in the trees, the shape of the hills, the path of a river, all of these are echoes of ice and fire, of warm times and cold. Next time you look at a map or walk down a city street, remember that the ground you stand on has changed many times before. Forests have grown and vanished, rivers have shifted, ice has come and gone. The world you know is just one chapter in a much longer book. So, what's the lesson? Maybe it's that nothing stays the same forever. Maybe it's that we're lucky to be here, right now, in this rare, warm window. Maybe it's that the story isn't finished. These cycles will keep rolling, with or without us. But for now, we get to be part of it. And in the end, that might be the most amazing thing of all. Out of all the possible worlds, we're here, living on a planet that freezes, thaws, and spins through space, watching the patterns, wondering what comes next, trying to make sense of our place in it all. If nothing else, the Ice Age cycles remind us to stay curious, to look for clues, ask questions, and never take the present for granted. The world is full of surprises, both big and small. Every day we walk through the results of ancient changes, some we notice, most we don't. The next ice age may be far away, or maybe it won't come at all thanks to what people have done. Either way, the story of Earth is still being written, and for now, we get to watch, learn, and wonder. So as you drift off, let your mind wander through deep time. Imagine the glaciers growing and shrinking, forests spreading, rivers carving new paths. Picture the world changing, slow and steady, always moving forward. You're part of that story too, a tiny piece of a planet that never stands still. Rest easy, knowing that change is the only constant. The ice will return, or maybe it won't. But the story goes on, and you, for this moment, are right in the middle of it.